that it has some of the problems that you'll see in real data sets. So we're going to talk about a Titanic survival data set. So in this data set, it records all the passengers of the Titanic or a subset of the passengers of the Titanic, and the goal is to find out if they survived or not. But before that, we're going to tackle that. We're going to talk a little bit more broadly about feature extraction. So far, we used only numerical features. So we had like a continuous measurement, and our data was just an array, one row per sample and one column per numerical feature. And yeah, for iris, we had these 4 features, these different length measures. Another kind of feature that's very commonly seen is categorical features. So here's, for example, color. So we might have also recorded the color of the flower, or we might have also, I don't know, if we're talking about people, we might record something like ethnicity or gender, and so these are not ordered variables that are continuous. These are like discrete different choices, and we need to sort of encode them in a way that makes sense for a machine learning algorithm. One way, and the way in which it's often these variables are stored, is by just numbering them. So red is 0, blue is 1, purple is 2, or something like that. Just number all your categories. That's okay for storing your data, but it's not a very good idea for applying a machine learning algorithm. If you just number the categorical variables, what you do is you imply that there is some ordering between them. And so colors are maybe not ordered in your application. I mean, they're ordered in a physical sense, but maybe that's not really meaningful for you. And most categorical values, they're just alternatives, and they have no in-betweens and no ordering. So if you just enumerate them, you will really distort the meaning of the data. So one way to encode categorical data is seen here. If you want to add a color to our iris data set, we could add 3 features which says, is the color purple, is the color blue, is the color red? And so you have a new feature for each of the categories. This is called dummy encoding or one-hot encoding, because only one of these, we have a group of features here, 3 features, and only one of them will be 1, and the others will be 0. This is a trick that's often done in statistical data analysis, though statisticians always use one less feature than there are variables, so they are not linearly dependent. We don't care about that. We just add, for each possible value of a categorical variable, we add a new feature that can be 0 or 1. There's several ways to how to encode these categorical variables with scikit-learn. And so in the end, we always want out a NumPy array or a SciPy sparse matrix so that we can feed this to our algorithm. If you're working with JSON data, like if you do web data or something like that, you always have dictionary-like data which looks like this. So for example, here you have 3 data points as a list, and each of them is a dictionary, where the keys are city and temperature. So here we have 3 data points that represent some cities, and we have a continuous feature, which is a temperature, and also what might be a discrete feature, which is the city. If we have dictionary structured data, we can use the dict vectorizer, which is a transformation method. So it's in the feature extraction module, and this is just a transformer. This transformer, you can do fit or fit transform, and it will transform the dictionary into a numeric array. So here you can see that the first 3 columns are the one-hot encoding of the city. So the first column corresponds to Dubai, the second column corresponds to London, the third column corresponds to San Francisco, and the fourth column is just the value of the temperature. You can call get feature names, and this will get back the names of the features. Another thing that's often very useful when you work with features is to derive new features. So here, basically, we derive 3 new 0-1 features from a categorical variable. But there's also other ways to derive features. We don't really talk much about this in this lecture, but it's, for example, using polynomials of existing features, using products of existing features is a very powerful way to generate new features for better predictions. So with these like basics about about features out of the way, we want to go into this Titanic data set. Or is there are there questions about like one-hot encoding categorical variables?
Yeah, so what if I can imagine, for example, an iris that had red and white as opposed to red and blue. One hot would exclude that possibility. Are there any cases where you can have 2 categorical values, say 1, because it's half red and half white as opposed to half red and half blue?
You could do that, but I would rather think that is like a separate category, a category that is white and blue. And so you have the combinations of color as a separate category. That's probably how I would model it.
Alternatively, if the whole flower is in this color, somewhere between red and blue, you can have maybe a numerical value with an intensity value, like going from red to, let's say, 0 to blue is 10, and 5 is somewhere in between. It would also work. Like if you can avoid the one-hot encoding and use a float variable.
I've tended to use pandas primarily in using the get dummies facility. Is there any material difference between that?
Oh, actually, we're going to use pandas get dummies now. So currently in scikit-learn, there's a thing called the one-hot encoder, but it only works if your data already is in integers. And we're currently like extending that to also allow strings. So often categorical variables are encoded as strings, as like red, green, whatsoever. And so we use the pandas dummy. Okay, so we start off by loading the data set here. So yeah, here we use the pandas library. We haven't mentioned that before, but this is a library that contains the class called data frames, which is very, very helpful for all kinds of data manipulation tasks. You can think of it, if you know R, it's similar to an R data frame. If you don't know R, it's very similar to just an Excel table. So you have rows, and the rows are numbered, and you have columns, and the columns have headers. And it also has a very good CSV reader, so we use that to read our Titanic data set and CSV. Titanic here that we get out is one of these data frames, and the columns are the properties that are in the data. So there's P class, which is which class the passenger was in, whether they survived or not. So that's the variable we want to predict. Their name, gender, age, number of siblings and spouses, number of parents and children, the ticket number, passenger fare, cabin, where they embarked, the lifeboat number, body identification number, and the destination. So we want to predict from where they were in a boat, whether they survived or not. So we definitely can't use the lifeboat number or the body identification number because they actually include the information whether they survived or not. If they have a body identification number, they did not survive. If they were in a lifeboat, they did survive, most likely. So we can also look at the data. So Titanic.head will give you the first, I think, 10 or something entries, and you can look at what they look like. At the entry. So here, this is the number of the entry, 0th row, 1st row, and so on. And at the top are the titles of the columns. And so we probably also don't want to use the name because the name is unique to each person, so we can't really learn anything from that. And the cabin is also like very specific to 1 or 2 people, or a family, as here. So we probably also don't want to use that. So we can try building a model using the class, sex, age, number of siblings, parents, the fair, and where they embarked. So this will be our features. This is again a pandas data frame. And so I call head to get the first 5. So this looks like reasonable data to try to learn from. So here we have P class as an integer, 1, 2, or 3. Sex is female or male. Age is a continuous value. And zip, SP, and parch, whatever, is integer. Fair is continuous. And embark is either C, Q, or S. So we have a mixture of continuous and discrete variables here. And so what we're going to do now is we're going to encode these categorical variables using the getDummies function from pandas. So here we do pandas.getDummies of the features. And then I use the head function to show the first couple again. And so that looks pretty good. So here now we have sex female and sex male. And can I scroll here? I'm not sure if I can. This is, okay. And we have embarked C and so on. And embarked Q and embarked S. So for each value of these categorical variables, we have a new feature. Maybe we want to think that the class of the passengers also should be more used as a categorical. That's sort of questionable. But you could think that they're not really a continuous number, but they're more 3 discrete different entities. But it's like, this is more or less a choice. But if you want to choose to one-hot encode this feature too, you can explicitly pass the getDummies function the columns you want to encode. So here I say, please encode P class, sex, and embark. And so in general, when you have a data set, it might be that some columns that are integers are categorical and some are not. And it's more or less a question for you, the domain expert, whether they should be categorical or continuous. Another issue here is that there's some nans in this data. So for not for all passengers, we had an age. And if we just try to apply a machine learning algorithm, it will just tell us not to do that. There's ways to cope with missing data. So the most easy way to cope with missing data is just drop it. So you can either drop the samples if a sample has missing values, or if a particular feature is mostly missing, we can just drop the feature. But this way we lose data, and we try not to lose data. What we're going to do here is we're going to use imputation. Imputation means we're going to put some value there. So we replace the value by something that we think would be a good fit. The easiest way, which we're going to use, is we're actually going to use just the mean of the column. If we don't know the age of the person, let's just say they have the average age of our data set. This is not the best thing we can do. It's more or less the simplest thing we can do. So, features dummy is a pandas data frame with the dummy variables. I know I use the values attribute, which actually returns a NumPy array. I could also use the data frame, but I'd like to work with NumPy arrays, so I use the values. So here, if I check, is there any nuns in the data? It says true, because there's nuns. And so we need to get rid of them. There's the imputer class in sklearn preprocessing that does this imputation, is filling in of missing values. And it has several strategies. And so by default, it uses the mean strategy. Not in this version, but in the current development version, there's also the possibility to add another variable that indicates if it was missing or not. So you fill in the missing value, then you also said this value was missing. This adds another feature. That's very useful because usually if a value is missing, that tells you something about the person. All right, so the imputer is a transformer, as other transformers that we saw before. So here we split our data into training and test set. We instantiate the imputer. We fit it on the training data, so it's very important that we don't use the test data information for the filling in of missing values. Then we transform the data, both the training and the test data. This fills in the missing values with the mean of the corresponding column.
What's the default method that the imputer is using?
Mean, using the mean. And now we can run a model on this. So here, what we're actually doing here is the most stupid model possible, which is the dummy classifier, which just predicts the most frequent class, which has probably died. Yeah. So predicting the most frequent class, we get 63% accuracy. But that's not very interesting. So as an exercise, I want you to try logistic regression as a classifier on this data set, and also the random forest classifier. We didn't talk about the random forest classifier so far, but it just works just like all the other classifiers. It has a fit method and a predict method. Are there any questions about this?
When you trade the one-part encoding, why does it come out as a float and not an integer? It's like 1.0, 0.0. It's either 1 or 0.
I mean, here, I'm actually not sure why pandas does this, but it doesn't really matter because NumPy arrays can only represent floats. Or the NumPy array has a homogeneous type, so, and we want it to be float because there are some floats.
So it just gets rid of the rest of the database, it ends up being that type.
Yeah. Other questions? Okay, so maybe we can, okay, we have like 10 minutes for the exercise, so you can try applying the two classifiers. So there was a good question, which was, do we really need two features to represent male and female? And the answer is no. So if you have a binary categorical variable, just one of them would be enough. But that's the way the pandas works. It's actually also the way the scikit-learn works. But if you already have a binary variable, you don't need to expand it into two. Okay, so maybe we can go on. So here, I just did imported logistic regression, random forest classifier, and fit it to the data, and then computed the score on the test data set. And I used the data finite, which is the one after the imputation. I also did a trick where I set the number of estimators higher. I think by default it's 5, and it's not so good. So I set it to 500, and it's better. So this is on the data how we encoded it. If I then I went back to the original data that was called features, and I removed the embark and parch variables. Did the train test split again, did the imputer again, and then ran it again, and the results on the random forest got better by removing these features. We're going to talk about how to find which features to include and to remove later on and in the feature selection part. Any questions about this so far? Yeah.
Why do they have to be random forest is supposed to pick out the most informative features? Shouldn't it ignore features which are non-informative?
Yes, but I mean, it's supposed to do that, yeah. But that doesn't mean it always succeeds.
Well, obviously.
And I mean, there's also some randomization involved, right?
With random forest also it appears that after a certain number of estimators the efficiency drops.
What? The
Efficiency drops.
what do you mean by efficiency?
Is greater than 500.
That's They're the same. You need to fix the random state. If you didn't fix the random state, your results will always be random. Okay, so I think that's it for this chapter, and we're going to talk about cross-validation next, I think.
Okay, now we are going to start the afternoon session, the actual one. So, yeah, in the afternoon session, we will talk a little bit more about a little bit more involved topics. I hope we are all familiar with the general scikit-learn API now. And one very important topic is cross-validation. That's basically making sure that our algorithm works well on real-world data, like it generalizes well to new unseen data. But on the other hand, also we sometimes want to tune our parameters. And what we've just done here in the exercise at the very end, we had a training data set and a test data set. And then we changed some parameters, like the number of n estimators in the random forest, and we took a look at the test score again. And I would say that it's kind of cheating, so because we are optimizing then also somehow to get the optimal test performance. So our test set is somehow leaking information, like we are a little bit with our estimate over optimistic. Maybe if there was a third test set, it wouldn't do better on the third test set. We are kind of a little bit overfitting to this test set because we tweak our parameters so that we get a good test result. And cross-validation is one way to kind of be a little bit more unbiased about tuning parameters inside a machine learning classifier, parameters of the algorithm. And we will talk a little bit about that. And in machine learning, we call like these parameters inside of the algorithm, like the tuning knobs, like this number of estimators in the random forest. We say these are the hyperparameters. Because, for example, a linear regression or logistic regression model, they have also internal parameters, like the weight coefficients. The intercept of a linear regression line would be one model parameter, or the slope of a linear regression line would be a model parameter. And to distinguish them from the tuning parameters, for example, the parameters of the algorithm, not the model, we call them hyperparameters. And so far, we usually use the default settings for hyperparameters. So we haven't seen that many yet. We will encounter many more in later sessions. And so just to recapitulate what we've done in this session, I'm not sure if I can bring a mouse up here. Oh, yeah, I can. Because of the microphone, I don't want to walk too far away. So what we've done usually here so far is we had a data set, data like the features and labels. We split it into a training and a test part. And then we used our training data. We chose some fixed hyperparameter values, the default settings in scikit-learn. We picked the learning algorithm with this fixed set of hyperparameter values, and we fit our model. So that was basically the model fitting, the fit train. And what we did then is we took our test data, not the labels, only the test data, gave it to our model, called the predict method, got a prediction, compared to the test label, and got a performance. And one thing we haven't, I think, mentioned yet, we briefly talked about the value of data because it's somehow, or it's usually in real-world applications, hard to get new data. So we want to be we want to make best use of our data. And typically, a machine learning algorithm will perform better the more data it has to learn from, more examples it has to learn from. So after we evaluated our model, there's actually no point or why we want to withhold this valuable test data, given that more data is always better, or not always, but typically. And so after we evaluated our model, we got our test score, we can just take the whole data set then and fit our model to this whole data set. And our model has more data to learn from. Of course, we don't know the performance then, because we don't have any additional test set, but it's usually better than just using the smaller training set. And this is also why when we split training and test data, both are representative. So it's basically just fitting the model with more data. That's typically done in practice, that after you've evaluated everything, you can just use the whole data set and fit your model. And then you can use your model and go out and make predictions on real new data. For example, if you want to predict, let's say, stock prices, then the stock prices of tomorrow that we haven't gotten yet.
So the idea is the performance of this final one is at least as good as the
Typically, yes. So there are learning curves that I think we will talk about it later. But you can, a simple thought experiment, what you can do is you can plot, let's say, your accuracy on the y-axis. And then you can plot it as a function of training size. And then you can do this with a validation or test set and subsets of the training set. What you typically then see is, for example, that your performance will go something like this. Maybe, let's say we stop here, we go like this, and maybe the test performance goes something like this. Let's say test.
Training performance would go down. Yeah, but training accuracy should go down if you increase it.
Yeah, it depends on how much you overfit. Yeah.
If you keep it model complexity, confidence should always go down, right?
Yeah, if you have, yeah.
You can go down like that.
Anyway, so okay.
But the
So
test one goes up, yeah.
what I mean is, if you haven't reached your capacity, if you see there's still a slope increasing, it would mean that your algorithm would benefit from more data. So you can basically create such a plot. It looks different really for different models and different data sets. But the point is basically usually you see that the test performance gets better with increasing data set size because the algorithm has more examples to learn from. And so the thing is, we also want to tune our parameters at some point. We have seen we have an estimator parameter in the random forest, and there are also different parameters in the logistic regression classifier, for example. We will talk about them more later, but one approach to kind of tune them but leave our test set untouched to the very end is holdout validation. It's probably the simplest method. So what you do here, instead of splitting it only in training and test data, you just split it into three parts, a training set, a validation set, and a training set. And then you use your training set basically to train your models. And then we can train different models. We can train, for example, one random forest with 10 estimators, one with 100, and one with 300. And so we get three different models, basically, three different random forest classifiers. And then, after we got our three classifiers, we basically use the validation set to compute the performance of each of them. It's like using the test set, but then the difference is that we have an additional test set in the end. And then we compute, let's say, the performance of our three random forest models, and we select the best one based on the validation set performance. So we select the best model. Then we, again, to make use of our data, we know the best settings now. We have the best hyperparameter values determined by using this validation set. And then we fit basically our learning or model, the same learning algorithm with these optimal settings. Let's say there were n estimators equals to 100. And then we get our model. And this model then is exactly like the approach is exactly like before. We use our test set to evaluate the performance. That should give us an idea of how it would perform on real-world data. And then again, because we want to use all of our data in the end, we fit again our model with all the available data and take it all to the real world. So the only difference between this approach and what we've done so far is that we have an additional set, a validation set, that we use to tune these hyperparameter values so that we don't reuse our test set. It's very important that we don't use the test set over and over and over again, because then we introduce a bias. So this is one approach. It's probably the simplest one. It's not always the best one. There are also downsides to this because you are using the validation set over and over again, and then your variance is pretty high because it really depends on how you split training and validation data. If you would, for example, change your random seed, you would maybe get different results. So it's kind of a high variance, a variable thing to do. And so a better way is, for example, k-fold cross-validation. In k-fold cross-validation, this is just an overview. We take, so imagine one row represents our training data set. And what we do is, when we do, let's say, 5-fold cross-validation, we have 5 iterations. And in each iteration, we split the data set into 5 chunks. So if we are at the first iteration, this would be a 5-fold cross-validation example. We would split the data set, our training data set, into 5 chunks. One will become the validation fold, and the remaining ones, they will be joined and will be a training subset. And then we compute the performance of when we fit a model to this training, to the gray area, and evaluate it on the blue validation set. And then we do this 5 times, but each time we have a different test or validation fold, and they are not overlapping. So basically what that means, each test set or each point, each sample in our training set will be at least, or will be exactly once part of the test set. So each data point will be used for testing at least once. And for example, in the holdout validation, without this cross-vault validation, we are really sensitive on how we split the data. So some points are always validation points, and some points are always training points. So this is more like an making use of all the data. And you do this then 5 times. You get 5 performance estimates, and then you compute the average of these performance estimates. Let's say it's 70%, 80%, 70, 80, 70, you get average of, let's say, 75% or something. And again, like mentioned this before, you use the gray part to train your model like before, and you use the blue part to evaluate your performance. So this is a K-fold cross-validation, and to see it in the pipeline, like in the whole data training and evaluation and prediction pipeline. So again, we start here. We don't create these 3 subsets anymore, like in the holdout validation. We have a data set. We split it again into training and test set. Then we use the training set here, do our K-fold cross-validation. For example, we can do it 3 times, choose different hyperparameter values. We get 3 different models. And then we have 3 different models. We select the one that has the best performance and use the best performing one to fit it on the whole training set. And then again, we use the test set to evaluate our model. Like the part 4 and 5 is just like before. So this is the most commonly used approach for hyperparameter tuning, tuning the parameters of a machine learning algorithm. And I highly recommend using it. Scikit-learn has a lot of different flavors of this and functions, which we will talk about in a few moments in the notebook, actually, with some code examples. And there's one more thing, we don't talk about it, but it's something maybe as a follow-up to keep in mind. There's also something called nested cross-validation, which is basically the same idea as K-fold cross-validation, but you have, it's pretty complicated, but like it looks complicated. It's actually pretty straightforward. You have an outer loop and an inner loop. So basically, this one would be 5 times 2 nested cross-validation. In the outer loop, you take one chunk and do another, basically K-fold. This is used to optimize the hyperparameters of a model, and then you evaluate it on the holdout data, on the blue one. And this is typically used for algorithm selection. We don't go into that into much detail in this tutorial, but usually you use K-fold cross-validation, the regular one, for hyperparameter tuning. But if you want to compare different machine learning algorithms to each other, then most people recommend nested cross-validation. There are many papers on that. It's more like an unbiased estimate if you use this approach. And yeah, let's then go to the notebooks, I would say, if there are not, if there are any questions. I'm not sure. Yeah.
Pragmatically, you use this on a subset of data. If you've got something that takes a month to train, you just change it into a 5-month project.
It's a good point. So you can also, of course, so there's a paper by, I think, Ron Kohavi. He tried different values for K and looked at how biased the estimate is and the variance of the estimate. I think tenfold was the best trade-off between model bias and variance. But it's really depending on how big your data is. The more often you split it, or the higher the K is, the more expensive it is to run. but also the maybe more meaningful your result, less variance you have in your results. So it's really also a trade-off between computational performance and the accuracy of your prediction, basically the accuracy of your accuracy estimate. So it's really like a trade-off. I would say 5, maybe a 10 is optimal. If it's too expensive, you can also use then basically the more classic holdout validation, which is then also used if you have computational restrictions. So it's really like, it depends on the application.
If I may add to this, so if it takes a month on your cluster, then I would use like holdouts. You only do train test split and have a single. If it takes a month on a single computer, the cross-validation is embarrassingly parallel. So just use 5 computers.
And also, yeah.
It still takes a month.
Yeah, scikit-learn, for example, you can use multiple cores of your CPU. So we will see in a moment there's a cross-validation method, and it will basically parallelize this across your CPU. So they will be then trained in parallel. Yeah, okay.
Was there another question?
Oh yeah, sorry.
Well, I sort of had the question on size and computational time, because a few times we tried to run this, we sort of just gave up because of the time.
Yeah, one problem is also, for example, if you use multiprocessing, it's not sharing memory as far as I know. So each of the processors will get a subset of, will get like a chunk of your data set. You have the main data set still in memory. That could cause problems.
If you're dealing with reasonably large data, it depends on what one calls large data, you're really going to bog down pretty quick.
Yeah,
In my experience.
Yeah, exactly. So there's always a trade-off between computational performance and really a good estimation of your accuracy. So you really have to find the right balance, I think, for your application. So if you develop a novel algorithm, publish a paper on it, I think people would be a little bit suspicious if you just do holdout validation. You want to do maybe some more thorough evaluation, but then sometimes it's not practical in a real-world application. So it's really like, depends on
What we've tried to do is just do this exercise on sampling to try and determine what was a good parameter set and then apply it to the larger set.
Yeah, that would be also one option. Yeah, that you work with a smaller data set that is representative of your true data set. Yeah, that would be also one way to do it. Yeah.
So if I may add this, the whole of CVPR, which is Computer Vision Conference, uses holdout validation. Like everything that's with neural networks, people don't bother with cross-validation because it takes a month to train.
Yeah.
I'm not saying it's a good idea. But you can publish stuff with holdout validation.
Will all change in a few years. Okay. It's weird. Okay. Yeah, this is basically what we've talked about, the k-fold cross-validation, that you split it in 5-fold cross-validation. You split it into 5 parts. So let's first initialize a simple classifier, the k-nearest neighbor classifier. We will work with the iris data set again, because it's quite simple and small, so computational efficiency should not be an issue at this point. And then we have the shuffling problem again. So we want to shuffle our data set before we do anything. All right. And this is an implementation of cross-fold validation manually, just to bring the point across. I'm sure if we really need it, but we explain it very thoroughly, but we can quickly walk through it. So what we do here is we create masks, basically. We have a mask that is a certain size of the test set, and then we basically assign it to zeros, and a certain set will be then become, certain values in the array will be set to 1, and this will be then our test fold. And we can then just do it like all the test points will be assigned to the test set or validation set. And the remaining ones, for example, the tilde symbol is saying everything but this test mask will be then training points. And we fit our classifier on this training subset, and we will compute the performance on this validation subset, and we collect these scores first. So we append them to a list. So we should get 5 performance estimates now. And and the masks, here's just a visualization by using Matplotlib of showing these masks that we just generated. So basically, first we took the first chunk. Iris is 150 samples divided by 3 would be by 5 would be 30 samples per fold for testing, and 120 samples for training in each time. We did it 5 times. And then we got 5 scores, and we compute the average score now. And as we can see, there's a slight difference between these folds. So that's also what I meant with if you use holdout validation, it's really sensitive on how you split your data. And you can see they are quite different. I mean, you have something between 90% and 100%. And so cross-fault validation takes the average of this, and it's, I would say, a more robust estimate than just using a point estimate that is very sensitive in how you split your data.
So I think I'm not clear about, so we have 5 different training classifiers, right? Each one are we going to use? So we have an average estimate, let's say 95%. When you go out and test it in production.
Okay, so we have 5 estimates, so this helps us to evaluate the performance. And usually we do this, we repeat this by changing the hyperparameter values and compare different settings of our algorithm. And once we found the one with the best average performance, we take our whole training set and fit it again. And then this would be then for the real world, basically when we fit it on all data. Right now, so there's basically a difference between like evaluation and having your final model. One step is really evaluating your model, and then later you fit your model on all data to make it as good as possible, and then you take it out to the real world, basically. Okay. Yeah, and scikit-learn has a cross-validation function, cross-val score, which will do exactly what we've done before automatically. So it's the setting that default setting CV should be 5, I think. I'm not sure. It's 3. By default, scikit-learn does a 3-fold cross-validation. And this is basically, this cross-val score is basically what we've done very laboriously up here. So it's a very convenient function that will do exactly that for us. And now we do the same thing with k-fold 5, k equals 5 cross-validation. So then we should also get the 96%, I think. We don't have the mean. Oh, it's a little bit different. Okay. So it also depends, I think, on how you set your random state. Doesn't it have a? Okay, it doesn't have a random state. Doesn't it have a random state? So it does always start at the left, right? Okay. I'm just wondering why we got different results here compared to here. Maybe no.
Because it's training twice. Cross-val scores training twice, and unit is
Right, okay. Thank you. Yeah, so by default, cross-val score, when we split our training set before, like in test and train splits, we used the stratify equals y to the target variable to stratify it. Here we didn't do this above, but the cross-validation score does it internally. Now also only for classification. And there are also classes for that. There's a k-fold class, which doesn't do the stratification. So I kind of briefly confused it with this one. And the stratified k-fold, which does the stratification. The shuffle split, what this one does is it draws samples randomly, so there can be so we can generate unlimited data. It's not like this one where only each test point becomes part of a training set once. For example, you would just pick, let's say, 30 random points in this first iteration, 30 random points in the second one, and so forth. And leave one out would basically be similar to k-fold, but each test fold consists of one test set sample only. You can imagine this is computationally very expensive because in this case we would have 150 iterations. So we start with a stratified k-fold, and this one basically performs the splitting of the data into 5 folds here. So the crosswell score above, it already does the evaluation, and this one gives us the indices of the split. So in the first fold, in the test fold, we would have these sample indices. In the second one, we would have these, and so forth. And as you can see, this is also why it's important if you use this k-fold to shuffle your data before. Otherwise, you will get also class imbalances. And this is a visualization how this looks like. So basically, the stratified k-fold, what it does, it takes from each sample. So for the stratified classification, it's not important to shuffle. It will, I think, do it by that it selects equal number of samples from each class, which would be 10, 10, and 10, and so forth. And yeah, that should work out of the box. And we also have a k-fold, which doesn't do the stratification. So it will take the first 31. So you have to be careful. For classification, I recommend using the stratified k-fold to maintain the class proportions. This is the same thing with 10 folds. And now to visualize the shuffle split, it will draw random samples from the whole data set at each iteration. So it looks basically like this. But at each iteration, it's also a sampling without replacement. So each sample only was drawn once as a test set in one iteration. There's a related thing called bootstrap, which we don't talk about here, but it's also a very commonly used method. And bootstrapping will draw samples with replacement. So you can have 2 times the same data point in one iteration, for example, in the same test set. It's usually used for computing confidence intervals of estimates, and more like statistical applications. So, and this is the same thing with 20 iterations. So it's more like a randomly split. Instead of we can basically set it to a very high number. We can generate much more data by that by randomly drawing. Because in k-fold cross-validation, we have the limitation basically that we run out of samples at some point. Yeah, and then we can use again the cross-validation score here, set it to 5. So basically, the crossval score, we can set it to 5, which will then automatically do stratified cross-validation. But we can also manually pass an object. For example, we can pass the shuffle split object, or we can pass the normal k-fold without the stratification. So any questions so far? Was probably a little bit confusing, but hopefully not. So by default, you can also set this to 5, basically. Then it will do the stratified cross-validation. And by using this CV that we initialized here by the shuffle split, it will do the same thing using this shuffled representation. So then let's do a little exercise and doing 3-fold cross-validation on the iris data set without shuffling the data. So I think that's a rather quick exercise. Everyone who is not done yet?
Who's still working on it? Who's trying to do it?
Oh, yeah, okay. No, anyway, so basically what we will see, I think the performance won't be as good because we didn't shuffle. So each fold will have the sample, like one class. and the training fault will have another class, and how do we predict based on that? If we fit our model on, for example, 2 classes, what we want to predict a 3rd class. So that's why we want to shuffle. Otherwise, yeah, we will predict something that the algorithm hasn't seen before, or the model hasn't seen before. Okay, so that's about cross-validation. The next topic, so finally tuning our algorithms, like tuning the parameters of our algorithm. So here we will talk about these hyperparameters, changing values of the learning algorithm itself. And we will use a method called grid search, which will generate a parameter grid to find basically the best combination of different values. Because there's not usually one parameter that we want to tune, there are multiple ones. And we want to find the best combination of multiple values. So, but I have an example about these learning curves here. And so here, actually I was thinking of accuracy, but error, but anyway. So one thing is our classifier can suffer from overfitting, or it can suffer from underfitting. Underfitting means basically that our model is too simple to capture maybe the information in the data set, and then it fails basically making good predictions either on the training set or or in both the training and the test set. So it can't even get the training predictions right because our model is not complex enough. Think of maybe the image data set, and we have a linear classifier. We can maybe expect that a linear decision boundary on a image data set where the image is kind of spatially encoded would be maybe not a good model to fit such data. So we would want to choose a more complex model, maybe a random forest or a neural network even. And the other problem is high variance. If our model is too complex, what happens is it will memorize the training set very well, but then it fails completely on new data or test set because it's so tailored to this particular data set that it doesn't generalize very well. And typically, how can we recognize this? I mean, if we plot learning curves as the number of training samples, we can see, for example, that the accuracy and of the test and training accuracy, they are both pretty low. They are not very good. And if you see basically a large difference between training and test performance, it means usually your classifier is overfitting. It gets usually better the more samples you give it. And then basically it's also a trade-off when we choose a model to find a good trade-off between bias and variance. We can reduce the variance by inducing bias, but also it can be bad if we introduce too much bias. So we want to find a good balance between the two. And that's what we will try to do in the notebook in a few seconds or moments. And just one more word on model complexity. So we can plot this learning curve as a function of the training samples. Or we can also do this as a function of a classifier parameter. We haven't talked about support vector machines yet, but they have a C parameter, which is the higher it is, the more biased our model becomes. And that means basically that our model will become simpler. And the lower it becomes, the more complex our model is. And as we can see in this plot, I think that's inverse regularization. C is the inverse regularization.
So low means simple model.
No.
Low means simple model.
So if you increase the if you increase the regularization, you get a simpler model, and this is the inverse. So if you have less regularization, or if you have a less parameter C, you have more regularization and then a simpler model. Yeah. I'm not sure why they did this inverse. It's annoying, actually, but anyway. Anyway, so basically the training and validation performance is plotted against this value of the parameter C. And basically the higher the value C, the less regularization you get. And then you tend to overfit more, because your model is too complex then basically. And the other way around, it's not doing so well if you add too much penalty to it or too much bias. This is in a very high range. It's just one example I plotted. I think I used the wine data set. We will talk about it in more detail later. And when we do grid search, what grid search basically means is we generate a grid of different parameter combinations. This is just in 2D, looking at two parameters. Again, sorry, we haven't talked about support vector machines, but this is one, the C parameter, the regularization, inverse regularization parameter, and this is basically the range of the influence of the samples, the gamma parameter. Let's just say these are two parameters, and we want to find the best combination of values. So here in this heat map, it basically shows that the white ones give us this is I think the accuracy gives us the highest accuracy. So a combination of a very small gamma parameter and a very high C parameter gives us a good validation accuracy, for example. We don't have to do want to do this manually, like looking at such heat maps, because we have multiple parameters, maybe 10 or 5 or 3, so we can't really visualize it, but can use scikit-learn. It has a grid search object that helps us with this. And let's switch to the exercise or notebooks. So here's an example of k nearest neighbors, and with different number of neighbors. So the smaller the number of neighbors, the more closely you see it will fit the data, but it will also be a more complex model. It will have a lot of fluctuations influenced by the individual points. And the higher the number of neighbors, the more kind of, I would say, insensitive to the noise. The regressor will become more insensitive to these noise points, and it will maybe more be closer to the actual structure of the data, ignoring these outliers. It will not be so susceptible. So a complex model, a complex regressor would be with a small number of neighbors, and if we increase it too much, we see our model becomes too simple. It will almost be not a straight line, but it doesn't really capture the data anymore, given that the blue one is the true data and the green one outliers are more like noise points. So we want to find, for example, a good trade-off between a model that is too complex, fluctuating too much, and a model that is too simple and doesn't capture the true function. And again, yeah, that's a chart comparing underfitting and overfitting. So again, in underfitting, we have both a bad performance in test and training accuracy. And if we are overfitting, we have a high training performance and a low test set performance. So in here, we start with a brute force search, basically. We have different values for nearest neighbors. Here in this example, we have 1, 3, 5, 10, and 20. What we could do is we could just do this with a k-fold cross-validator that we have seen in the previous section. Because it's a regression example, it's not certified, so we just use a regular k-fold object. And what we see then is different accuracies based on the average cross-validation score. And if we look at that, we would say maybe 3 or 5 neighbors or maybe 4 neighbors would be a good choice here. Because again, like one neighbor is overfitting the training set, so our cross-validation average is very low. The accuracy is very low. And also the other direction is if our model is too simple, it will also be bad on the training and test set, so also a lower cross-validation score. So it helps. It's a brute way, a force way to basically change one parameter and choose the best hyperparameter, which would be maybe 3, 4, 5. We can plot this in a validation curve, like I have in the slides before, and we can see basically the overfitting here, the huge gap between training and test. And here that it performs even worse than random, I would say. Oh no, it's not a classification. But it performs also badly on the training and test set if we have too many neighbors because our model is too simple. Now we think Andy will talk later about support vector machines in more detail. Right now, let's just assume we have a support vector regressor here. It's a support vector machine for regression. And we can do the same thing. So why we picked this as an example is because it has more parameters to kind of illustrate the point that we create a grid of parameters. And here we have the C parameter, the inverse regularization parameter, and the gamma, the influence of the individual training points. And here we kind of created a grid. So we have now 2 parameters, and we want to find the best combination. And again, we can look at the scores at the very right, the average cross-validation scores. And we have to we can see that this one is maybe the best one here. So a combination of a very high C value and a very high, or the highest gamma value in our grid would correspond to the best score. Maybe it would become even better if we would increase both values. That would be one way, also a brute force way to generate such a parameter grid. And now to make...
So that score is essentially like R squared, right?
Yeah, R squared, sorry.
What is negative score?
So R squared can also be negative. If you look at the equation, it's not like you have the R and square it. It's do you remember the equation, Andy?
Oh, it's a mean square error.
No, it's R squared here. It can become negative if one second.
There's no reason for it to be positive, basically.
R squared, the sum of the square root of the
R squared.
That depends on the model. Here's like it's a prediction. Yeah. It's just a residual.
So it's basically, maybe you have to look at it. I forgot. Long time since I took stats. But basically, it's not computed as the R times R, which would always be positive. It's basically with the sum of, it's basically the mean squared error without the mean. And for the total samples and
It's
square.
divided
Yep.
by the mean. And 1 minus that.
Yep. Okay. So again, we have then a grid search cross-validation object in scikit-learn, a class, which basically does this automatically, what we've done before. But it's more convenient because we typically don't have only 2, we have sometimes 5 parameters, and then we have 5 nested loops, which is kind of first tedious to look at, tedious to write, and also it's not running in parallel. And the grid search CV also parallelizes this because each parameter combination can be evaluated independently. There's no reason why we have to do this sequentially. So basically, we can set up a parameter grid. And in the parameter grid, we have to specify, it's basically a dictionary. We have to specify the parameter we want to tune. For example, here the C parameter and the gamma parameter. And then we provide a range of values. Typically, a list, you can use the NumPy linspace or A-range functions. So you don't have to write it out. But you can tune basically every parameter in this object then by just providing the parameter name as a string and some values for it. And the CV here is basically the cross-validation. You can put a number in there, like 5 or something. Here we use our k-fold because we don't want stratification here for our regression example. And verbose will just gives us more output. The higher the verbose number, the more output we get, which we can look at and hopefully learn from. Okay. And then the grid search object will basically behave like a normal estimator. It has a fit method, a predict method, and a score method. And by default, it will fit. So it will by default do the cross-validation, collect the results, and the best score that it was achieved during the cross-validation will basically be kept as the best estimator, which is then available as a grid.bestestimator_. And this is automatically refit on all the training data, not only on the last training fold, but on all the training data that we gave it. Was there a question? So we set the verbosity level a little bit high here, but then we get some output that we can maybe take a look at. And if we have a large data set, this will be generated incrementally, so we can check basically the progress of the grid search. If it takes too long, for example, if we only see this first line for, let's say, 20 minutes, we maybe want to think about changing something here, like reducing the computational complexity of the search. Because the more parameters you have, of course, the larger the number of combinations you want to evaluate. It's basically a combinatorial explosion at some point. And yeah, then you can look at the scores, but also the grid search automatically provides you with the best score. But one thing we haven't used here, I think, is a njobs parameter. So usually by default I would maybe try to run it on one CPU, but you can put njobs in here equals to 1, which will use all your CPUs. Or you can also say I will just run it on 2 CPUs here, because I think this thing only has 2 CPUs. But it will also, so I think if I put something like 20 in here, it would crash or something. So -1 is just using all cores though. So maybe why not? If nothing else is running on a machine, you are doing machine learning. Yeah, then, like I said, there's a best estimator, and can basically look at it. So that would be basically our best estimator, the one that achieved the best score in a grid search. And it gives you also the parameter. So for C equals 10 was one parameter we tuned, the gamma 1, and other parameters that we didn't tune here. But these are then the defaults. You can also tune them during the grid search if you like. But this would be your best parameter combination. And then it's already fit on all the training data. So you can use all the data you gave it. So you can use the predict method then to use this best estimator to do predictions, which is then very convenient. And there's also an attribute best score, which tells you what the score was like. And best parameter combination you can also look at. Okay. Yeah, so again, above we didn't split it into training and test sets. So it was maybe more like a naive example. When we do this over and over again, our estimate will be over-optimistic because it has seen the data before that we used to evaluate it. So like I mentioned in the slides before, it's actually better to split it into 2 parts, a training set and a test set, although we use the whole training set to do the cross-validation. That's because we have an additional step of tuning hyperparameters. What was that question? So the same thing again with now a test and training set. So that is basically our test score. It's not the average cross-validation score. We can maybe, do we have it below? No. We can maybe compare it to the cross-validation score. Which is even a little bit lower. So, and the best parameters are again C, 10, and 1. Although we just gave it a smaller set this time.
So usually you would expect the cross-validation accuracy to be higher than the test accuracy, but it's not a big data set and there's no exception.
Yeah, it's probably also sensitive in how you split it.
Yeah. And we only did a single split into training and test set. Where sort of the nested cross-validation could come in.
Yeah, for example, I just changed the random C to 1. You can see it's now vice versa. That's more what I would expect. It's not a huge difference, but the cross-validation score would be slightly higher. But it's a good sign if they're very close to each other. That means that we found a good parameter combination during cross-validation that doesn't overfit. So we can do the same thing now with a shuffle split. It's very similar, but instead of k-fold, we use the shuffle split.
Because in particular here, shuffle split does only one iteration. So this is actually just doing a split of the data in 3 parts, and to just have a single validation set. So if your model trains for a month, you probably want to do this.
And a very similar score here. And it would be interesting seeing if we got the same parameters. Yes, so it's quite of a robust model then, actually. It's a very, the best parameter combination is not very sensitive to how we split the data, which is actually a good sign. I'm not sure why the solution is here, but looks like that. It was the one. Okay.
Remove the solution.
Yeah.
And then do it again.
But you have to do it too, right?
Yeah.
Yeah.
Or we can do like a different, like random forest insertion.
Let's, yeah.
Or linear SVC and search C. I was tired last night, sorry.
I think it's fine. We have a lot of material to cover later, so maybe this one will be a bit quicker. Yeah.
Confused by this because like we're overfitting and underfitting, but it's based on noise, and the noise can vary, right? Wouldn't the underfit and overfit be on the actual digits themselves?
So the thing is,
The true kind of.
so the noise sample, if there's a noise sample and outlier, it may only be present in a certain data set, so we don't want to assume there's always the same noise point. So we kind of want to ignore it somehow. We don't want to model this point because it can look totally different in a real-world data set because it's noise. It can be anywhere. So we don't want to put too much emphasis on this. We want to have a simpler model that is not so much affected by the noise, but by the core structure of the data, basically. So, so maybe it's simpler for a classification example. If you have like something like this, 2 classes, I think it would be better to fit maybe a general, like a linear line, rather than doing something. Rather than doing something like this or something, because these in a new data set or in a test data set, these might not be exactly right here. We want to more like capture the general trend that X samples are more to the right and the circles are more to the left, something like that. So basically, simpler model is usually better, but to some extent, if it's too simple, then it doesn't work anymore. For example, if we have something like maybe here a linear model, I would say, wouldn't work so well if we do something maybe like a straight line here. Here it would be maybe better to draw something like, maybe it's a little bit too much, but something like a curved line or something. So it really it really depends on the data set. Sometimes a simpler model, usually a simpler model is better, but not too simple, so that it performs well on both training and test data sets. It's basically why we usually compare training error and test error, or validation error and training error, or accuracy.
And the minimization of the score is basically the average variance of all the type of parameters?
So usually So the average score is basically based on these folds, on these 5 folds, and then we get a score for each parameter combination. So for each parameter combination, we have 5 scores for each fold if we do 5-fold, and then we take the average. Maybe I can also. So if we have C equals 1 and the gamma 100, we get 5 scores, let's say 0.6, 0.7, 0.6, and 0.7. And our cross-validation score would be then 6.5, right? And we do this then for multiple parameter combinations. Oh, sorry. And we do this then for multiple parameter combinations. And then we select based on this score, the average cross-validation score.
Really break up the exercise.
Yeah, we should break up the exercise. I think hopefully everyone did at least a little bit. And it's basically doing the same thing that we've done before with the digits data set, using different values for the k nearest neighbors and the grid search object. And here we're using 5 folds, will be stratified then, because it's a classifier. If we are using a classifier, it will automatically do the stratification. And we got a pretty good score here on the test set. It's 0.99 by just choosing one nearest neighbor. Okay, the next topic would be scikit-learn pipelines, and this is something Andy wants to talk about. This is basically 1 second, and you can. So that will be basically making this whole thing more convenient, because right now we only optimized a classifier, but we talked about before about feature scaling or PCA and having a pipeline that does everything automatically, that we don't have to do it manually. But Andy will talk about this in more detail. And, up here.
I thought we were going to take a break now.
Break? Okay.
Or,
I have no idea. We could take a break.
Yeah, I think we should take a 15-minute break.
I need a coffee, definitely.
Yeah, there's coffee. Yeah.
Often we need to pre-process data before we can use machine learning. We saw the scaling, for example, of data, and damn it. So I just realized we used the text data here, which we didn't talk about before. But let's skip over the text data. So the idea here is that we often have several transformers that pre-process the data, and then we have a final model like a classifier or a regressor to do a prediction task. And this is a very, very common pattern. And so there's something inside scikit-learn that helps you make this pattern more easy. So actually, let me just, it's unfortunate that we didn't do the text stuff, so let me do this separately. So sorry about that. So let's do this on the digits data set. So for just believe me, for a support vector machine, if you put in the digits, it's not going to work very well. Or I can show you. Yes, sorry for being a bit slow. So here, using this SVC, a support vector machine, didn't work very well. But if we scale the data before we apply the model, it will actually work much better. So we're going to use the min-max scaler. and then we use x train scaled is the scalar fit and transform. This is the same as calling fit and transform sequence of x train. And x test scaled is and so now if I fit the SVM, it works much better. Hopefully. So scaling the data before applying the support vector machine made a huge difference. So this was this 10-class digit classification data set, and we went from 46% correct to 95% correct. Okay, so we want to definitely scale our data. But we also know like the SVM has like a lot of parameters to tune, so let's try to tune the parameters. So we can define a parameter grid. Okay, let's say we just search over C because I don't want to, or maybe also gamma. All right, and now we can use a grid search and search over the parameters. And we saw the scaled data works much better, so obviously we want to use the scaled data. And so we can do this. Unfortunately, this is not really a good idea, so this runs for a second, I guess. So what we did here is we, obviously in the last line, is we scaled the data and then put it into the grid search. The grid search runs cross-validation. That means inside the cross-validation, we have the scaled data, but we estimated mean and variance from the whole data that we passed into the grid search. So inside the cross-validation, the part that is in the test part of the validation fold, we already used that for estimating the mean. So that doesn't change the scaling too much, but it is kind of cheating. So if we had different pre-processing steps that might be really, really fundamentally wrong doing the pre-processing before the grid search, we should use the cross-validation that the grid search does at the outermost loop. We should first split the data into training and test set in the grid search, and then do all the pre-processing steps at once. And so I have this nice picture here. So we should always do cross-validation about around everything that we do, not just the final classification. And so pipelines enable us to do this grid search or cross-validation over everything at once by putting all the steps in just a single estimator. So what we can do is, instead of doing this fitting the scalar, transforming the scalar, and so on, we can do we can use the make pipeline function and put in the min-max scalar and the SVC. And this will return this pipe. This pipe is now an estimator. It's a classifier. It's a classifier that consists of two steps, applying the min-max scalar and then doing the SVC. So if I do pipe dot fit xtrain ytrain dot score. So if I run this line, what do you expect to be the outcome? Maybe I hope I wasn't going too fast. Any idea what will be the accuracy of this model? So this is exactly the same as fitting the min-max scalar, transforming the data with the min-max scalar, then fitting the SVC. So the outcome will be the same as we had before. It will be 95% accurate. But we do everything in one step, because all the steps we have are encapsulated in the pipeline. And and now we can run a grid search over this pipeline instead of running the grid search only over the last step. So we can use the same grid search that we had, that I wrote somewhere here. But instead of using the SVC as the estimator, we can use the pipeline. And then we give it the original data that we didn't scale yet. There's one more caveat here. Because we're using the pipeline instead of the support vector machine, we have to tell the grid search which step of the pipeline we want to adjust the parameters on. And the steps in the pipeline are named, as you can see this here. They're named by the lowercase class name. So there's one, the first step is called min-max scalar, and the second step is called SVC. And so we want to adjust the parameter sin gamma on the second step. And we say this by giving the step name, double underscore, then the parameter name. So if you're grid searching a pipeline, you have to write it like this. And now we can run this. And this now does proper cross-validation and grid search of the pipeline that consists of both steps, the scaling, pre-processing, and the model search. So maybe let's go back and go a little bit more inside what what the pipeline does. So in fitting, again, so let's say you have two transformations. I call them T1 and T2, like let's say a scalar and a PCA or something like that. Or often you want to impute and then scale. So let's say T1 is impute, T2 is scale. What pipe.fit does is it fits the first step, then with the original data and the labels, then it transforms the data. You get a new representation of the data x1, say the imputed version. Then you use x1 to fit the second step, the scalar, for example. You transform using the second step, you get x2, another representation of the data. And you use this final representation and fit the final step, which is a classifier. During prediction, you just use transform on all the steps. So you do transform on the imputer, you get a new representation of the data. You do transform on the scalar, you get a new representation of the data. And then you use prediction, do the prediction using the final model.
This relates back to 14, but are you supposed to be able to use the same parameter grid for any classifier or different classifiers?
No, I mean the parameter grid is specific to the parameters of the classifier.
Okay.
So C and gamma are parameters of the support vector machine. The k-nearest neighbor classifier has only one parameter, which is n neighbors.
All right.
Okay, other questions about pipelines? Was I going too fast? Which part is unclear? So it basically just changed these transformations so that you can put all the transformations into a single scikit-learn estimator. The benefit of this is not only that you have shorter code, which is always nice, but also that you can use this estimator then inside cross-validation and grid search. Okay, so maybe it will become more clear when you do the exercise. So we already used the Boston housing data. So I want you to create a pipeline that consists of a standard scalar and a ridge regression, which is just, or you can use a linear regression if you want. Maybe you just use a linear regression. They're nearly the same. And apply it to the Boston housing data set. Then you can also try adding a third step in, which is using standard scalar, polynomial features, and then ridge regression or logistic regression. And then finally, search the degree parameter of the polynomial features. So then you have at the end you build a three-step pipeline, and you search over the parameters of the second step. But start off with trying the two-step pipeline. All right, so maybe we should continue because we don't. Oh, we have some more time left, but not that much. All right, so here I did it with ridge, but ridge is more or less the same as linear regression for now. I think I explained the difference in the next notebook. So here I did the standard thing. I loaded Boston. I called train test split and made a pipeline out of the standard scalar, polynomial features, and ridge. In the pipeline, I used a parameter grid where I do polynomial feature, which is the name, lowercase class name of the polynomial features, and double underscore degree for the degree of the polynomial. So this basically, so for these, if someone didn't look it up or doesn't know, so this basically creates all possible polynomials, or multiplications of this degree as features. So if you have x1 and x2, degree 1 would not do anything, I think. Degree 2 would do x1 squared, x1, x2, x2 squared. x3 would do, all the others too. And so you can see that, so here we fit, and it finds polynomial degree 2 is best. I also saw some people having 1 or 3. Depends a little bit on the random state. So, and on how many cross-validation repetitions you do. The data sets are not that large, but I think 2 is actually the most reasonable one. This means you expanded the features quite a bit. You made the model more powerful. You added complexity, but not too much complexity. And so the test score is actually pretty good. So if you do this without the polynomial features, I think it will be in the 60s. But some of you try that. Any questions about this? So this is really quite powerful, and I would suggest you use pipelines and grid searches all the time. There's usually pre-processing steps, and if there's pre-processing steps, you should use pipelines. And this is actually quite a complex workflow that we have here. But it's not that much code. So if you can understand this is like a full analysis of a problem, basically. Maybe you would grid search a little bit more, or try a little bit more, but this is like a very complex analysis workflow, actually, that we built together here. And so mastering this pipeline and the grid search, I think, are very important. So all steps, I forgot to mention this, all steps except for the last one need to have a transform method. So you have an input for the next one. So I couldn't add logistic regression after this because Rich doesn't have data output. Or what was it that you wanted to do?
I think that makes sense. So if you, in that case, if you wanted to build a pipeline that had, say, both the standard scalar polynomial features, and then you want to apply multiple models, you would just have the pipeline for the data transformation piece, and then you would do that in 2 different models.
Well, you could create just two pipelines for 2 different models, or what do you want to do with the models? Do you want to evaluate them separately? Then I would create 2 pipelines. If we want to average their outputs, then you can do voting classifier, which actually allows you to combine multiple classifiers into one to do like an ensemble.
Can we
you cannot grid search over the steps of the pipeline. So basically, what you want to do is you want to like change rich for something else, and you want to search over that. That's not currently possible in scikit-learn. I'm working on making that possible. Or, I mean, it's not that hard, but I need to argue with people that that's a good thing to do. I mentioned that before. There's a project called AutoSK-learn that I really like. And it's not my project, but I'm going to talk about it on Friday. This basically searches automatically over all reasonable pipelines. So you give it the data, and then it goes off and searches for a couple of hours. That's kind of fun.
So, question, like, can Pipeline handle the missing value imputation?
Yeah, so I mean,
Any function like you can just plug in?
Pipeline can do anything, but okay, Pipeline does nothing basically, so it can do anything. So if I want the standard scaler would barf on missing values. So before I can apply the standard scaler, I need to impute the data. So I need to do imputer here. Add a step before the pipeline doesn't really care what you do.
How about kind of the dummy variable stuff? You can also
So you can do, you can use the scikit-learn one, which is one hot encoder. You can not easily do the pandas one because it's not a transformer. If you implement the pandas one as a transformer, which is probably around 5 to 10 lines of code, then you can also use the pandas one. Other questions? So actually, yeah, many people do implement their own custom transformations or classifiers that work with the scikit-learn interface to use things like pipeline and grid search. And we're not going to go through this here, but there's documentation online, and it's very, very simple to build your own classifier or your own transformer. Basically, they have to have a fit method, and they need to have a transform or predict method, and then you're good. And then you can use your own algorithms with these things, or your own transformations. All right, so let's move on. So before we go into more depth about the models, I want to talk about model evaluation and scoring metrics. So we talked about accuracy in R² so far, and I want to talk about some more different methods. So okay, here, what happened? This is a little bit boring. So here, that's what we did so far. Basically, this is the digits data set. We split it into a training and a test part. We built a model, and then we can score it using the score function. This is like a very, very aggregate view of this, what happened on this data set, right? These are 10 classes, and we have many, many predictions, and we have many possible predictions that we could have made, and we aggregated them to this one number. We can, wow, and the number is not the same as in the text. So if you want to, we have a more detailed view, we can use the confusion matrix. Here, the confusion matrix, each row corresponds to one true class, and each column corresponds to one predicted class. So that means the things on diagonal are correctly predicted, and the things off the diagonal are confusions. So for example, we took this 2 here, and twice the model thought on the test set that this 2 was 7. Maybe a reasonable confusion. And we can also see that there was a 3 here that was taken for a 2. And there was a 4 that was taken for a 3. That's kind of weird. But you see this model did pretty well. There were some confusions, but mostly they're just single cases. What is the most difficult one seems to be there's a lot of 8s that were taken for 2s. So it does seem to be particularly difficult. The model is very simple. This is a linear regression model. But you can see where the mistakes were made. That might help you inform what kind of features to add or what to change. Yeah, you can also do a heat map plot. This is not a very... You can also do a heat map plot. And yeah, sometimes that's more readable. And then you see directly, oh, here, this is kind of bad. Or maybe also this. But this is the opposite. This is like a very, very fine-grained view, and we can't use this, for example, for grid search, because now we have, these are 100 numbers, right? Yeah, these are 100 numbers, and we can't really compare them directly. If we have one parameter setting, we get 100 numbers. We have another parameter setting, we have 100 numbers. Which one is better? So there are a couple of ways to aggregate this that are not as, they're different from accuracy. And first I want to talk about how this works for binary classification. So binary classification is if you have exactly two classes. If we have two classes, we call one class the positive class and the other class the negative class. And the positive class is usually what we call the class of interest. So if we would want to do spam detection, spam is probably the positive class. If we do cancer detection, cancer is probably the positive class, even though we might think it's not very positive. And so if we have, I wish I had a picture here. So if we have binary classification, the confusion matrix looks something like this. So we have the positive and the negative class. So this is true positive class, true negative class, predicted as positive, predicted as negative. And so these are called the true positives. These are the positive examples that are classified as positive by the model. Then there's false negatives, the ones that are true, but the model said they're negative, but it was wrong. The negatives that were classified as positives, these are false positives. And the negatives that were actually negative, these are the true negatives. So this is for binary classification, the confusion matrix, and these four quantities are sort of the raw material that all the other metrics, or most of the other metrics, are made up of. And so here in the notebook you can see there's precision. Precision is true positive divided by true positive plus false positive. So this is the fraction of the positive. This is sort of how likely, if we said something is positive, how likely is it to be actually positive? So precision tells you something about how many false positives that we do. If we have very few false positives, we have a high precision. If recall is true positives divided by true positives plus false negatives. So this is how many of the actual positives did we get as true positives. This is also called coverage. So if you produce a lot of positives and you capture a lot, you have a good recall. If you are very selective and you capture only the ones that are really true positives, you have a good precision. And there's usually a trade-off between the two.
Maybe you could give us an example, a real-world example, like
yeah.
email spam classification or breast cancer screen, when which
Yeah.
one is more important?
Yeah, sure. So usually both are important, and there's a trade-off between the two. But sort of, for example, for cancer screening, which is sort of a common example, if you make a false negative, that would mean a person has cancer, but you didn't detect it, which is like very bad. So whereas a false positive would mean someone that's actually healthy, you think has cancer. You can send them to a doctor. Doctor will find out, oh, they don't have cancer. You spend a little bit of money on the doctor, but it's not too bad. So in this case, it's much more important to find everybody that has cancer. So recall would be much more important. It would be important to cover all the people that are actually sick, just so that we can give them treatment. While giving some false positives, like sending a couple people to the doctor that actually don't need to go to the doctor, not so bad. And so often there's sort of some cost associated with if you have, if you're running a business and you do email campaigns or something, then usually there's like dollar values you can attach to all of these. Like if you make a mistake of this kind, it costs me that many dollars. If you make a mistake of this kind, it costs me that many dollars. And then you can find out how you want to trade them off. if you don't actually have your cost matrix or your manager refuses to give it to you, then what you can do is using the F1 score, which is the geometric average of precision and recall. So this basically takes both into account to some degree. And the formula is wrong. Plus in the numerator, right? Is that correct? Yeah. I think so too. So this is, yeah. So F1 is sort of, for binary classification, often works a little bit better than accuracy. However, this is a quantity is sort of hard to interpret. So accuracy is very easy to interpret. It's the fraction of things you got correct. This one. Sorry.
It's a geometric mean, basically.
Yeah. I was never good at the different means. Sorry about that. Yeah, so, I mean, but this quantity is kind of hard to interpret. So there's a function called classification report in scikit-learn that computes all these quantities for you, like precision, recall, and F-score. So these are usually defined for binary classification. Here we had the digits data set, which is 10 classes. And in this case, we can compute, if we make each class a positive class, what are precision, recall, and F-score. So here, if we look at 0 versus all the rest, our precision is 0.98, and recall is 1. So that means we got all of those zeros, for example. And we also got all the 4s. I mean, here, these are all very good because the task is very easy. But you can see how you get a relatively fine-grained view of how well we're doing with each of the classes. Support just means how many samples are there in this given class. Questions about that?
What is the zero command index?
That's a class. So this is if I make class 0 the positive class, and the rest is the negatives. And this is for class 1 being positive, and so on. So for each class, I have a precision and a recall and an F-score. So these metrics are particularly helpful if you have these asymmetrical costs, like in the cancer example, where one is much more important than the other one. The other case is if you have class imbalances. So the number of samples in that class.
So, like, extending your example, they could be different types of cancer. And, right, like the non-competition.
Yeah.
Okay, I'm sorry.
Wait. This is a digits data set. This is the digits data set.
Oh, okay. But it could just be
It could any multi-class.
So, but basically then take the average of all the individual class precisions or recalls, and are you talking about macro and macro?
Not really. I mean, it's not a notebook, and yeah, I don't know. Yeah, I mean, you can look at the average of the F1 score over all the classes, which this gives you some overall measure of how well you're doing. I mean, so multi-class comes up in the real world often, and the classes are never balanced. So you should always kind of look at these, because if the classes are imbalanced, then accuracy doesn't mean a lot. And so let's say we have a class balance that is 1 to 9. So I'm actually now doing a binary classification task where I do classify the digit 3 against all the other digits. So there's 9 times as many other digits as there's the digit 3. This is actually a very mild imbalance. So as is shown here, like if you do ad click prediction, people don't click on ads ever. So for every impression that you show an ad to someone, like every thousandth or 10,000th time someone clicks on it because they had like some seizure or something. It's true. People with mental health problems click on ads. That's most ad clicks. I'm not sure if it's funny. Anyhow, yeah. So here before we had this very balanced data set, but now I want to do a data set that is imbalanced. So X is again the digits, and Y is if the digit is 3 or not. This is a very silly imbalanced data set, but just bear with me. But it's just an example. So if I now do cross-val score on a support vector machine, it gives me 90% accuracy. Is this a good classifier? Who thinks this is a good classifier? Hands up. Has 90% accuracy. Okay. You think? Okay. Who thinks it's a bad classifier? Why?
90% of your stuff isn't a 3.
Yeah. So if I always say it's not a 3, I'll get 90% accurate. So it's as good as always saying it's not a 3. So it's probably pretty bad. But actually I would argue that it's you can't really say a lot about the classifier just looking at accuracy. So here, yeah. So let's compare this against the dummy classifier that always predicts the most frequent class. It's as good, according to accuracy. So here again, now we have 90% are non-3s and 10% are 3s. One thing that I like that is, we could use the F1 score. The F1 score would help us a little bit here in being more precise. But what is even more sensitive is what is called the ROC curve, or receiver operating characteristic curve. And so we're going to plot this here. So the ROC curve, what it does is it takes in, so here I fit the model with some parameter gamma, and I look at the decision function. So I mentioned this briefly earlier. The decision function gives us the uncertainty estimate of the model. If it's very low, it thinks it's a negative class. If it's very high, it thinks it's a positive class. And how high or how low it is gives you some measure of the confidence of the classifier. Then if you now have like this continuous spectrum of is it a 3 or is it not a 3, what does the classifier think? Usually you make a prediction by saying if the decision function is greater than 0, I think it's a 3. If it's lower than 0, I think it's not a 3. But that's sort of an arbitrary point, this 0. You could shift this, and you could change the threshold. You could classify more things as 3 and less things as 3. If you classify more things as 3, you'll get a better recall, but a worse precision. Or, in this case, sorry, maybe better, you get more true positives, but you get also more false positives. What the ROC curve shows you is, as a function, if you change the threshold, if you try all possible values, what will be the trade-off between true positive rate and false positive rate? The ideal curve is the one that is shown here in blue, more or less, where you're in the top left corner, which means you have 0 false positives most of the time. You can achieve a true positive rate of nearly 1, so you get all the positives without getting any of the false positives, which gives you like very good trade-offs. If you do a random classifier, you have this line in the middle, which says, well, I'm always, if I classify more points as positive, I'm as likely to pick up a positive as a negative, more or less. So what this ROC curve measures is not so much a single classification, it measures more a ranking of the samples. This will be very good if the samples are ranked in the correct order. It doesn't matter if they're like, would be all classified as positive or all classified as negative, as long as they are ranked in the correct order, so that all the negative ones are ranked below the positive ones. I get a curve that is in the upper left corner, that means good. So what I tried here are 3 different values of gamma. Yeah, doesn't really matter much what they are, but the accuracy that I computed, the accuracy for all 3 different values of gamma is 90%. So they're all equally good according to accuracy. If I look at the ROC curves, though, like the blue one is nearly perfect, while the red one is as bad as random. So there's a very big difference in how well they rank the samples. If I want to compress this ROC curve down to a single number, which is helpful for grid search and stuff like that, you can compute the area under the curve. So basically, you compute the integral under the curve, which is called AUC, area under the curve. And if you use this as measure, you can see that for the red one, it's 0.5, which is the worst possible outcome. And it's 1. I mean, it's 1 up to floating precision for the blue outcome. So blue is perfect. Red is the worst possible. According to accuracy, they're the same. I find this quite striking. So, so I think you can't really say if it's a good classifier or a bad classifier, because a very good classifier and a very bad classifier have the same accuracy.
The accuracy is only depending on the actual ones. If they got the actual ones right, it doesn't look at all.
No, the accuracy. No, it depends on everything. So, I mean, one thing is that the AUC doesn't depend on the threshold. So as long as the ranking is correct, you can get an accuracy of 1. So this probably ranked classified too few points as 3, but it still ranked them correctly. So basically, you have like the classifier creates this line, like how much are you at 3? And then there's lots of 3s here, and then there's lots of not 3s here. And probably what the classifier did, it cut it off here, and it says the. No, sorry. Oh, sorry. I think it's more likely the other way around. It cut off here and says these are 3s, these are not 3s, and then so the accuracy is not that high, but the ranking is still pretty good, and you could actually adjust this very easily. So, and for imbalanced data sets, because you usually have some particular trade-off of recall and precision, you can change this trade-off by changing this threshold. And so usually the threshold is not at the right point anyway. So if you want to pick your own threshold, you shouldn't use the threshold of 0 to evaluate your classifier. So if you have imbalanced classes, I would always use AUC to do grid search for the parameters, for example, because it's way more robust.
So, am I correct in assuming that the blue line is indicating absolute accuracy?
Yeah, I mean, there's like some things here. So there's probably 2 or 3 that are confused, but it's basically perfect. Yeah. Other questions? All right. So, okay, so we have this area under the curve, which is a nice metric. Now we obviously want to use this for grid search and cross-validation, and the way we can do this is using the scoring argument. So the scoring argument can be a string. For example, ROC AUC for the area under the ROC curve. And then instead of using accuracy, which is the default, it uses area under the ROC curve for scoring. And it tells us this is pretty good. So there's a bunch of built-in scoring metrics that are listed here. You can find them all in the documentation and what they're good for. They're, some are for classification, some are for regression, some are for clustering. And that's all like in the documentation, you can find these. But you have like the F1 score accuracy, MS, mean squared error, mean absolute error, yeah, precision recall, adjusted run score, average precision, a lot of things you can think about.
Just a suggestion, one thing we found that started making things a lot easier for us was when we used tests, when we had labeled tests, we could just determine the mean positive of the test set and determine whether the model gave us a higher or lesser mean average. And that told us instantly whether we were getting a lift from the model or not.
Yes. I mean, that's the calibration of the model, more or less. Well, okay, it's a little bit simpler than calibration of the model, but sort of, yeah. I mean, what you can actually do is you can convert this to true probabilities if you want. So you can, there's something like what's called calibration, which gives you actual good probability estimates, which is even better, but it's a little bit more involved. So you can also, like someone just asked me this question, you can also implement your own scoring functions. If your field has a specific way of saying how good something is, you can implement your own scoring function. I call this one my accuracy scoring, which is the same as accuracy. The interface that you have to fulfill is you need to accept an estimator, which is a trained model, and basically some data and labels. And then you can use the estimator to predict on the data and compare it to the labels, and here compute the mean, so this is just the accuracy. And then I can pass this callable to the scoring as the scoring argument. And you could do arbitrary things in here. The only requirement is that higher should be better for grid search.
Why is the scoring function a function of model and certain shouldn't the function just predicted labels and output labels?
No. So one reason is, for example, if it was like this, you couldn't implement the area under the curve because the area under the curve needs uncertainties. Well, it's a different kind of prediction that the model makes. But you could also use like penalize the model if it's too complex. So you have, this is more flexible basically. And there's reasons why you want it more flexible. Yeah, here for example, this is like slightly silly. So here I said the first part here is accuracy, and the second part is how many of the coefficients are 0. And I want most coefficients, as many coefficients to be 0 as possible, because I want a simple model. And then I can do a grid search using this. And I search over, do I want a linear model with L1 or L2 penalty? And we're going to cover this in the next notebook, but L1 makes everything, it makes a lot of things 0, L2 doesn't. And so it will select the one that makes many coefficients 0. So if you desire some specific property of your model, you can include it there, and then the grid search will take it into account. So how much time do we have left? It's until 5:30. Yeah, maybe we can do this. So maybe yeah. So this exercise is about average precision, or average per class average per class accuracy, and maybe you can implement this average per class accuracy as it's explained here. And it's basically just a very simple function.
So that's something scikit-learn doesn't implement yet. I think people didn't want it.
There's no reference paper.
Oh.
There's like one reference paper with like 3 citations.
But I think it makes kind of. Can you scroll a little bit? I think it makes kind of sense in some cases. I would probably prefer F1 score or something. But it's basically if you have imbalanced classes, you can compute an average accuracy. So in this case, given this confusion matrix, you have different number of samples. You have 90 samples in total. And what it basically does, it's computing the average for each class, the number of correct predictions, and then it takes the average because we have 3 classes over 3, and it's the average class accuracy. I thought it was maybe a nice exercise to implement a scoring function. Maybe it's a little complicated. I don't know.
Should we do it or should we skip?
I don't know. Maybe it takes too long. Can you scroll a little bit down? I think I have a simpler example.
No.
Based on this one, computing the error or implementing a scoring function to implement the average accuracy, but since also Annie mentioned that there's probably no reference paper for that, maybe we don't really have to go through this. But
Yeah, okay, but maybe we skip it for now because we don't have that much time. And we have like, yeah, we're not going to finish anyhow. Any questions about performance metrics?
What if you have outputs that can have multiple labels?
Sorry?
What if you have something that you have multiple labels firing at the same time?
Multi-label classification. Yes, there's metrics for that too. Look at the documentation. I mean, I don't know. There's specific metrics just for that case. But I'm not an expert in these, so it's actually the documentation will know more than I do.
Are there ways to score the speed of executing the model, or classifying something with the model in case that becomes?
So it's not possible to do this in the scoring. In the 0.18 version of scikit-learn, which is the next release, the grid search will record all of this. So you can look at it. But I don't think it's possible to... You could hack your classifier to store it in the classifier, and then the scoring method could read it out of the classifier. If you want that. Other questions? Okay. So now let's talk about, actual machine learning. So first I want to talk about linear models a little bit more. So linear models are sort of the most simple and most widely used models. And they all employ formula that looks something like this. So in particular for regression, this is a simple case. So let's talk about regression first. So in regression, the predicted output is a linear combination of, or the training features weighted by some coefficients. So the model has some coefficients and some intercept, and the coefficients are the weighting of the input features. So this is just the inner product of a data vector and the coefficient vector. And so here I'm going to make a data set, or not. Sorry about this. This needs to be cross-validation. I hope this doesn't happen. So you make a regression data set which has 200 samples and 30 features, and 10 of the features are informative about a target, and the rest is noise. And so now we want to build a linear model. So this data actually came from a linear model. So there's actually a true linear relation between the output y and the input x plus some noise. And we actually have the true coefficient that generated the outcome. So the most simple model that we can try to build is linear regression. Linear regression is the least squares fit. So here the weights are called, or the coefficients are called W in the formula, and the intercept is called B. So they're like alternative names. And basically, W transpose times X plus B is the prediction the model makes on Xi. So Xi is one data point, it's a vector. And we subtract Yi from this. So this is just the error in prediction, and we sum up the squares. And we find the W and B that minimize this prediction error on the training set. So what it says is, I want W and B that make good predictions on the training set according to the squared norm, or Euclidean distance. That's sort of the most simple thing you can do. And yeah, we already had that. So we trained this on the training data set and tested on a test data set. One thing you can see here is, so the data set is relatively small and has relatively many features. And we can see that on the test set, we do quite well. On the on a training set, we do quite well. On a test set, it's pretty bad. And so we really overfit the data. If we look at what the model with the true coefficients, the true coefficient is the true model that actually generated the data. So the ideal R-squared score would be 0.6. So our training set really overfit, and our test set is really bad. So we want a more simple model than this. Or we can also look at the coefficients, actually. Now let's look at the coefficients. So here, the blue coefficients are the true coefficients. How do I scroll here? Oh. Oh, no, no, it's more, I can't use a Mac thing. Just now I scrolled sideways, now I can't scroll sideways again. Whatever. Okay. It's not that important. I mean, I can also go, yeah, maybe I just do inline and everything looks ugly. All right. So here blue is the true coefficients, and I sorted them actually by their size. So here these ones, the first 10 ones are actually not equal to, are unequal to 0, and the last 20 ones, they're all 0, so they don't have any effect on the outcome. And you can see, and the green are the coefficients that were estimated by logistic regression, by linear regression. And you can see, yeah, they look kind of similar, but sometimes they're way off, like here, or here, or here. And so we saw on the small data set, linear regression way overfit. But this is synthetic data, so we can just generate more data. We can see, how does this look like if we add more data? And so here, the training set size is on the y-axis, the r-squared is on, sorry, it's on the x-axis, the r-squared is on the y-axis, and we see that for small training data sets, this is really bad. And as the training data set becomes larger and larger, it becomes okay. And so actually, 0.6 was, I think, the optimal that we could get. But so maybe we want to do better in this regime where we have very few samples, and by having a less complex model. One way to have a less complex model is ridge regression. Ridge regression looks very similar, but in addition to trying to fit the data well, we also want the model to be simple, which is the second half. This basically says, not only do I want to fit the training data, I also want W to be small. So W is the vector of coefficients. Adding this to my minimization problem means the second part will be 0 if W is all zeros. So the second part, this alpha times W, times norm of W says, push W to 0 as much as possible. And alpha is a free parameter of the model, which trades off how much do I want to fit the data and how much do I want it to be simple. If I make alpha infinity, the model will be 0. If I make alpha 0, I'll have linear regression. And so I can, on this curve that we had on underfitting versus overfitting, alpha moves me along this curve, so I can control how complex my model is. And so here, this is actually this curve. Again, here's alpha 100, means a very simple model. 10 is a little bit more complex. Even more complex and even more complex. And you see the training score goes up with a more complex model, but the test score, there's a sweet spot here. And after that, we are overfitting. We can also look at the coefficients. Again, so this is the same plot as before. Yeah, I have 4 different values of alpha, and in blue the true coefficients. And what we can see is that if I increase alpha, all the coefficients shrink towards 0. So here you can see this is the complex model, less complex, less complex, less complex. Everything goes towards 0 as I increase alpha, as we would expect. What's also interesting in this plot is that depending on how I set alpha, the sign of the coefficients might change. So some people like to interpret coefficients. Be warned, if you look at this one, for example, or at this one, so for some particular, or no, sorry, just to change the sign. This one changes the sign. So depending on how I set my regularization, the model either says there's a positive relation with the effect or there's a negative relation with the effect. So that makes it very hard to interpret this coefficient. And so you should be very careful about interpreting coefficients this way. But we got quite a bit better by using rich regression. Again, we can look at, if we change the number of training samples, how does rich fare versus linear regression? And you can see that the training set accuracy in the beginning is lower because it overfits less. But the test set accuracy is higher because it overfits less. And so these two curves are closer because we limited the complexity of the model. As we add more and more data, it basically becomes the same as linear regression. Is there a question so far about linear regression, rich regression? Who has seen rich regression before today? Oh, quite a few people. Half. All right.
If I have like a really big data set, does it make a difference? Or
No. I mean, it can. So I wouldn't, actually the rich regression is usually simpler to solve, depending what kind of solver you use. But it also depends on number of features versus number of samples. So if your data set is like very big and has 10,000 10,000 samples, but it has 100,000 features, then you definitely need to use rich. So it depends more on the ratio of samples versus features. If you have 10,000 samples and 10 features, then it doesn't matter. So another linear model for regression that's very popular is the lasso, which looks very similar to rich regression, only that we have, oops, I'm sorry. It's my alarm. I should wake up. Wake up, everybody. Instead of having an L2 norm here, or Euclidean distance, we have an L1 distance, which is just the norm of the absolute values. What this does, curiously, is it makes some entries of W be exactly 0. Yeah, I'm not sure if I should go into like why this is, but that's definitely what happens. So again, all the entries of of W are pushed towards 0, but some values are pushed exactly to 0. With rich, that never happens. They were all kind of smushed down a little bit. With lasso, the ones that are small are completely cut off at 0. This is helpful either if you think that only very few of your features actually are important. So you put in a whole bunch of stuff, but you don't really think they're all important, but you don't really know. Or if you want an explainable model. If you have 1,000 features and you use rich regression, all of the 1,000 features will have an influence on your output. That's very hard to interpret. If you use a lasso, maybe only 5 of the features have non-zero coefficients, so that's much, much easier to interpret. It mostly works well if actually the data does depend only on a few of the features. Here we created the data set specifically so that the data only depends on a few of the features, so lasso actually does quite well. So here we see a similar curve. Too much regularization, we are underfitting, there's a sweet spot, and then we start to overfit. So this is a function of the parameter alpha that says how complex the model should be. Sorry? It does element, I didn't understand the last word. Yeah. basically, they have no influence at all. It's sort of automatic feature selection in a way. We can again look at the coefficients, and so here this is interesting because you can now see that if we increase regularization, so the dark green is again high regularization, you see some of the coefficients are exactly 0. Even for alpha equal to 10, which is the best model, I think, yeah, alpha equal to 10, like a lot of the coefficients are exactly 0. And that means the model found out these features are actually not important. And so this is quite nice. I mean, if all of the features were important, this would not really help us.
Is it pretty common to do all of these and do a comparison like in this next block?
Yeah, so there's actually one model that I don't have here, which is called Elastic Net. And Elastic Net has both of these, and you trade them off. So you have one parameter that says how much L1 penalty and one parameter how much L2 penalty I want. And you can basically grid search over everything. And usually that does the best. I mean, it's like a superset. It's a more complex. You have more parameters to tune, but you have more freedom. So because I did the, I think I need to increase the figure size. That's probably too big. Yeah, there we go. So here's a comparison of linear regression, ridge regression, and lasso. You can see that with more and more data, they become more and more similar. The training score in lasso actually is lower everywhere, so it overfits less. But because the model actually is what we call sparse, some of the coefficients are actually 0, the model does quite well. So this was all I wanted to say about linear models for regression. For classification, the things look very, very similar, only that we also have, so we want, this is for binary classification. We do the same thing, we do the inner product of the data with some coefficient vector plus an intercept. And then we ask, where did it go? Is this greater than 0 or not? That's the threshold I was talking about earlier. So if it's greater than 0, we say it's positive, otherwise it's negative. That's how we do binary classification with a linear model. This is a simpler minimization, but it's not least squares, and it's usually like a bit more tricky to do, so I'm not going to go into the math too much here. But again, there's two classes that implement this in scikit-learn. I mean, there's more, but there's two main classes: logistic regression and linear support vector machine. And they both, so the difference between them is how they penalize making a mistake. So they, one uses a logistic loss, the other one uses a hinge loss. And these are both sort of replacements for the square difference for the classification setting. And both of, this is great. Clearly I ran this before. Both of them have, again, allow for these penalties that make the coefficients go to 0. Only these don't have a parameter alpha, these have a parameter c, which are more or less 1 over alpha, which is what Sebastian complained about. So low c means push everything to 0. High c means don't push it to 0 so much. So I could do coefficients plot as I did before, and you would see that with low c, everything would be very small, and with high c, everything would be much bigger. What I thought is a little bit more interesting is a different visualization for classification. So here we have a two-class classification data set, and this is a linear SVC model trained on the data. Here, this is the decision boundary. So this model says everything above this is blue and below is red. If we make C very small, that means like a very simple model where stuff is pushed towards 0 a lot. The model basically captures the overall shape of the data. Like blue is at the top, red is at the bottom, so let's do a horizontal line. But it makes two mistakes. if I allow the model to be more and more complex, it will try to make less mistakes and can put more and more weight on each individual data point. So we can see here, as we increase C, this decision boundary tilts and at the end gets this red point correct too. So now we make less mistakes, but it looks kind of weird to me at least, because I would rather think that the blue is at the top and red is at the bottom. So I probably like this one better. But decreasing the regularization means that the model can put more and more emphasis on each individual data point. It can't actually predict all of them correctly because it's not possible in the setup, but it tries as hard as it can. Whereas here, with small c, it tries more to capture the overall shape. The linear SVC also and logistic regression have a penalty parameter, which you can either set to L1, which means be like lasso, try to make some actually 0, some coefficients, or the default is L2, which means push everything towards 0. So that was all for binary classification. For multi-class classification, it gets a little bit more complicated. So here, let's say we have this data set of 3 classes, red, green, and blue, and we want to distinguish between these 3 classes. If we fit a linear support vector machine model to it, we'll get 1 coefficient vector per class and 1 intercept per class. So there's 3 classes, 2 features, it's a 2-dimensional data set. And so I have 1 coefficient vector for each class and 1 intercept for each of the 3 classes. So what this provides us with is basically 3 lines. There's 3 lines here that separate each class from the other classes. So we learned to classify green versus the rest of the classes, red versus the rest of the classes, and blue versus the rest of the classes. And then if we want to classify a new point, basically they all compete, and the one that says positive the most strongly will win. So things here will be classified as red. Things here will be classified as blue. Things here will be classified as green. Well, the one that says the line is closest to, so there's like a triangle that goes like this. So maybe you can, as an exercise, do logistic regression to classify the digits and grid search the C parameter. And additionally, think about what will happen if you change alpha in these curves that we did above here. So here, in this learning curve, we have set regularization for origin alpha. What do you think will change if I make this alpha larger or smaller? First, think about what you expect, then try it out and see what happens. Questions? Here in for ridge, let's say we change this alpha to 100. What will happen to the blue curves, green curves? You say they get further apart? Other opinions? So increasing alpha means I push everything more to 0, which means the model will get simpler. And that means both will probably go lower, but they will also actually become closer together because both they will need to be more simple on the training and the test set. And this was not, wait. And I changed what x and y means, sorry. I need to go back and find my x and y. Yeah, and you see both of them got way below the rest. So if I make alpha 1, what do you think will happen? Yeah, if I make alpha 1, they will both be closer to linear regression because I decrease the effect of the regularization, I decrease the penalty, so now basically it's the same as linear. And if I make it like even smaller, it will be identical with linear. All right. So I think you're going to skip the SVMs because they're not that interesting. Well, they're kind of interesting.
Maybe disagree, but yeah.
Well, they're theoretically interesting, but they don't. Have you used SVMs recently?
Once in a while, but only the RBF ones. I mean, for linear, it's usually logistic regression.
Can we do it just like real quick, because we talked about it earlier and I have no idea.
Okay, just the slides or?
You want to do it or should you can do the slides if you want?
Okay, so it's actually your part, but I do it. No, sorry. So basically, Annie mentioned before what the support vector machine basically does. In a linear case, what happens is basically we want to find a hyperplane or a linear boundary in a case of a 2D data set that separates our classes well. And typically we have a margin. So what we want to do is we want to basically place the decision boundary in a way that it is falling just between these two samples. We don't want to be too close to one or the other, because then the model generalizes better. Because imagine in a slightly different data set, the point is maybe a little bit shifted upwards, and then it will misclassify it. So it's probably ideal to place this boundary just in the middle. And that's basically what the linear support vector machine does. And then these points that fall onto these lines are the so-called support vectors. That's why it's called a support vector machine. And so that's what we are doing here with a linear support vector machine. And typically we use in practice often the kernel trick. For example, RBF kernel, it's a radius basis function kernel, a Gaussian kernel. And the kernel trick is, yeah, a little bit tricky, but just a brief overview of what the kernel trick does. So basically what we do is, if we can't separate our data in a two-dimensional or a linear space with a linear boundary, so in this case it's simple, but if we have a higher dimensional data set that is not linearly separable by any boundary, we can just project it into a higher space. You can think of the polynomial features. We can create new features until we find a space, we project our data up until we find a space where we can just slice it with a linear line. So, but this is very expensive to create new features and to find one that works well. So the kernel trick basically avoids this. There's I don't want to go too much into the math here, but there's a so-called a gram or kernel matrix, which is using the pairwise similarities between different features. But the point is basically what happens in the kernel trick is that we are projecting our data onto a higher, in this case, it sounds weird, but it's an infinite dimensional subspace. And in this subspace, we basically can draw a linear decision boundary or plane, and then separate the samples. In this case, what I did here is I used polynomial kernel. So I had 3-degree polynomial kernel and projected this data, the 2D data, up into a new 3-dimensional space. And in this space, I basically just lifted the blue samples up with a function like this kernel function phi. And in this space, I can draw a slice through the data. And this is basically what the kernel SVM does. But then it kind of projects it back onto the original space. And if you project it back, if you take away the dimensions, you will get a nonlinear decision boundary. And for example, imagine you have just a linear classifier. You can't really classify these samples with a linear line. So the trick is basically to generate a new hyperdimensional subspace, feature space, where you can draw such a linear line and then just project it back. So that's why it's called the kernel trick. It's a trick where you lift it up, slice it, and then project it back to get a nonlinear decision boundary. So, okay. But now I think we will talk more about decision trees and tree-based learning and ensemble methods, something that we haven't talked about yet before, I think. So decision trees are a little bit different from the linear models we talked about. And so what is a decision tree? A decision tree is basically, just like the name suggests, a tree of questions, if you will, and we make a decision at each node. So this is a decision tree, for example. I'm not sure I made this up at some point. So I can put it to work actually in the real life. It's sometimes useful. So do I have work to do? Yes or no. If I have work to do, I stay inside. If I don't have work to do, I look at the weather forecast. If it's sunny, maybe I will go to the beach if I would have some in Michigan, and things like that. So we make basically decisions at each. So these are, the white ones are basically our features. And this is a three-part split. Scikit-learn implements binary decision trees. So each split is in Scikit-learn a binary one. It's just to illustrate the concept of a decision tree. And when I applied it, for example, to Iris, I get something like this. So I look iteratively at the features. For example, the petal width, is the petal width smaller than 0.75? If it's smaller, then I go put these samples into this node. Here are 34 samples. And if it's larger, I will put it here, and there are 71 samples. So basically split it iteratively and spread out your data set, and you make, if you don't set a limit on the depth of a tree, it will split until your classes are pure, which means it doesn't misclassify anything anymore, or if there's no way to distinguish them, it will also stop. But here I think I have a depth of 3. I set a depth of 3, so it won't go further. And I think we have it in the notebook to generate such a tree using, what is the library called? A GraphVis, I think. I'm not sure if we have it. Yeah. I'm not sure if we have it in the notebook actually, but there's a nice documentation on the scikit-learn website. And someone actually made this prettier in the new version. It looks not black and white anymore, it's colorful. And so the values here, what they tell you is basically 34 samples are in class 1, or class 0, 0 samples are in class 1, and 0 samples are in class 2, so it's pure here. All 34 sepal, Iris setosa are here based on the petal width, only as a feature. And maybe you're wondering what this entropy thing here means. That's basically an internal kind of metric to make the split, to decide where to split and how to split. And another important point I wanted to mention here maybe is, here I used categorical features, and scikit-learn also supports, of course, continuous features. So here we just, in Iris, for example, we set a threshold on this linear scale. So for example, smaller than 0.75. Doesn't have to be binary, the feature variable. And yeah, there are different entropy measures, but just to illustrate the basic point is that these are basically like convex, and the reason why we, for example, don't want to use the classification error for growing a tree is because of this kind of linear behavior here in this spike. So if we split a tree and we split a parent into 2 children, we measure basically the entropy, which is how mixed the classes are at each point. And if we use the misclassification error, it can have the same classification error in the sum of the children and the parent, and then we would stop growing the tree. So basically you can imagine this as 2 points here. Let's say this point, and if you take the average, it's here. And that would stop basically growing the tree because it doesn't improve anymore. And through this convexity, basically, we can then still continue growing, although we apparently didn't make a point improvement, but overall we will make later in a later level maybe an improvement. And so the entropy and Gini coefficients, or its G impurity actually, that just means it's a measure how mixed our classes are. If we have a 2-class system, if our class is totally mixed at 0.5, so 0.5 one class, 0.5 the other class, it will be maximum, and we want to minimize. This is just basically how the decision trees work internally. And yeah, that's about decision trees, and we will also talk about ensemble methods. And we had, for example, the random forest previously. And random forest is basically just an ensemble of decision trees. You can think of the n estimator variable that we had set before as the number of decision trees we provide to the random forest. For example, if we set n estimators to 100, it will use 100 decision trees. And for each decision tree, if we provided the training data, it will select a subset of the training data. So it will draw a random subset. And it's with it's a bootstrap one, so it's with replacement. So each of the 100 trees will have a slightly different training data set in the random forest. And then also, not only for the samples we draw a random one, we also draw random features. So that's why the random forest is probably called a random. It's basically a forest of random trees, maybe. And each tree gets also a feature subset. And these feature subsets are not overlapping. For example, if we have a iris data set, we have a random forest with, let's say, 3 trees. Each tree will get a slightly different subset of samples. They can overlap to some extent, though. But each tree will have one individual set of features. For example, the first tree will have sepal width and sepal length. And the second tree will have sepal width and petal width. And bagging is basically, I would say, a little bit older than random forests. In bagging, it's basically just a random selection of samples. And in random forest, we also randomly select the features. And the idea is basically behind random forest and bagging is we fit a lot of complex decision trees. But if you grow a large decision tree until the leaves are pure, you will likely overfit your training data. You will split until everything is pure. And if you have new data, you probably will overfit because your model is way too complex, way too deep. And through this random sampling, you basically introduce you make your model, you average your model, you make it simpler, more robust. So in a decision tree, you have one tree. In a random forest, you have 100 trees. And each of the 100 trees will make a different prediction. And then by majority vote, you will select the majority sample. So for example, if you have 3 decision trees in random forest, 1, 1, and 2, like the predictions of a class, it will by majority vote then select class 1 as the prediction. And it's basically like asking an ensemble of experts to make your prediction. It's kind of more robust than just asking one decision tree. And boosting is kind of the opposite approach, I would say. So here you don't grow a lot of complex decision trees, but you grow very simple. You take the simplest decision tree, just a decision stump, just one decision stump, and then you train it, and you look if it makes a mistake or not, and you take a look at the examples it made the mistake on, and then you assign a certain weight to it. You make these examples more important. You give it to a next decision stump, and it will try to get these ones right. I will have a figure on that later, so to illustrate it. So random forest and bagging, these are basically methods to average very complex models to make a more robust prediction. And boosting is basically boosting a very simple model to learn a more complex function or decision function. So yeah, just to illustrate maybe bagging a little bit. So I said we are drawing samples with replacement. So if we have 3 bagging rounds or 3 decision trees in a random forest. So if our sample indices are 1, 2, 3, 4, 5, 6, 7, each one gets a random subset. So but there can be, because it's with replacement, there can be overlaps. For example, test sample 2 can be included twice and 3 times and things like that. And some samples may not be included at all. For example, the 5 doesn't appear here. And then for each bagging round or each decision tree in a random forest, you train a separate classifier or model. And then this will be just averaged. And in practice, this looks like that. So basically, one decision tree that I just grew till infinity, till everything was pure, may look like that, the decision boundary. So it's a very complex one. And if you think about it, also decision trees can only split basically perpendicular to the feature axes. So this one is a decision tree on, that is a different data set. It's a wine data set with alcohol and hue, classifying 2 different kinds of wine or grapes. And as you can see, this decision tree is very complex. It makes this weird decision here to just get these two right. And I'm not sure if we have new data, if this is not just noise. Maybe we want a simpler decision boundary. And by averaging multiple decision trees, by this bagging, we can kind of basically make this less complex. There's still some complexity here, but we don't go down here. So I think it's like a more robust way. And for boosting is basically, like I said, like boosting a decision stump and making it more powerful. So a decision stump is just one decision. So for example, splitting along one axis. And we do this, and then we misclassify, for example, these two blue ones. So in the next round, in the second round of boosting, we emphasize these especially. So we want to get these right, especially these two. So then we have one in the second one, and then we get different ones wrong. We get these three blue ones wrong now. So we will then put an additional weight to these ones to get these right. And we continue this, and at the end, we kind of combine all these three, or in this case, these three decision stumps to one more complex model. One that splits here, one that splits here, and one that splits here. And it looks then basically like that. So that's basically this boosting thing. And now let's go to, do you have any questions so far? Ah, yeah. Yeah, I think boosting can more likely overfit than, for example, a random forest and bagging. So that's also something you have to be careful about. But again, so it's probably less overfitting than a simple decision tree. So you're boosting this simpler model that is too simple for your data to make it more complex. But also there's a limitation to it. But yeah, it's I would say more readily overfitting than maybe bagging and random forests. And I think yeah, it's a XG boost. I'm not sure if you heard about it. It's extreme gradient boosting machine, which is also an ensemble, which some nice extras. And this is probably one, based on what I've seen so far. I'm not competing Kaggle, but Kaggle winners usually nowadays use XG boost. So, and very, very complex models. I think there was this famous story, the Netflix story, that they had a $1 million prize on the best model or something. And people built such complex models, like not one ensemble, but an ensemble of ensembles and stacked and stuff like that. So it made a very good prediction in the end, but Netflix said, yeah, sorry, but that is too, you get the money, but we can't use it. It's too complex. Our engineers can't implement that. So they went, I think, with a second or third solution, which was a little bit simpler. So yeah, there's also the trade-off, of course. I mean, if you think about it, one decision tree, okay, but if you have 1,000, your training time, it will be much more expensive to do the classification and the training. So it's also, depending on your data set, a trade-off between computation complexity and performance. So sometimes even if a random forest may perform better on a certain data set than a linear model, maybe you want a linear model because it's almost impossible to fit 1,000 trees. Maybe you have memory issues. So it's basically a trade-off you want to think about, that you also have to weigh in computational efficiency. But now to the actual notebook. Yeah, and you can also use a decision tree for regression. So how this works is basically you do the same thing as with spreading the classes, but a little bit differently in that, I mean, you want to, it's called variance reduction. It's kind of, you want to reduce the variance at each node of your target variable. So you want to have the values as similar as possible. And then, for example, if you have a decision tree, and you have one point, let's say you split it into something. You have basically the decision tree with, let's say, 3 target values. Here's something like the decision, let's say, greater than 5. No and yes. And if you build a decision tree for a regression, you will basically split your decision tree based on the target variable, which is continuous. So you will get basically continuous values in here. And then you don't do a majority voting or something. You basically take the average at that node. So you compute basically the average value, and this is how you basically do the regression. So if you want to predict a sample, if you have a new sample, you go down through the decision tree, you arrive at this node, and then you pick the average value as a predicted point, which can be very noisy or very like zigzagged, like in the k nearest neighbors with k with k equals 1. So we start again with a very simple data set here. And let's do the decision tree regression here. So here we have a tree with a depth 5. So we have 5 levels that we split our data on. And for this prediction, it will be not a linear bound or linear decision fit, linear fit anymore, but a very zigzag boundary, because you're basically influenced by all these points in the area. You take always the average. And sometimes it can help to fit such a complex function. In this case, I would say it's probably not the ideal choice. Random forest can average this a little bit out, that it becomes smoother. But also one limitation of decision trees for regression, I would say, is if you predict something that is bigger than any value that you had in your training set, it will always be bounded by your largest value in the training set. Because if you think about, you take the average, or if you, let's say you have a 5 or something, and this is your largest target value, and if you ask, is my feature greater than 5, okay, predict 5. But if your feature is 5,000, it will still be 5 because this is your largest value. So you can't really go much beyond something that you had in your training set. It's one limitation, I would say. So we do the same thing. We had a decision tree regressor here. Now we will use the classifier, the decision tree classifier. You can also say a maximum depth. So I can just, maybe for illustration, change this to 1. It will be a very similar, simple boundary. And the boundary basically increases with the complexity, which is when the overfitting problem arises, and that is something then the random forest helps with. So the rest is basically our familiar interface, the splitting. So the only thing is we changed compared to previous notebooks is that we are using this decision tree classifier now. And this is then basically how it would classify this data set with depth 5. It's maybe too complex for this data set. It makes always these horizontal splits, but maybe a few too many. If we decrease it, it will be a little bit simpler, a simpler model, which is maybe better. But doing this by hand is kind of tedious. You can't always visualize it. So that's why random forest is also so popular. So I would say, for example, this would be a better way. It's not such a complex model. And yeah, here we have a nice interactive function where we can, what I've done just manually, can change the depth of the tree. No, not really. Have you tried this? I don't know. I haven't tried this.
Showed that there's still an error with the
Oh, okay. Right PNG. Yeah, but this one, yeah, works basically. Yeah. Maybe I just haven't installed the package here. Anyway, so does someone get it to work on their machine? I think you need the graphs, right? Yeah, I ran everything at home on my other computer. It wasn't a mistake.
Yeah, mine knows.
Oh, okay. Yeah, I think you need this, what is it? Graph. This. It's an external visualization software used for graphs, usually. And yeah, you would have to install it. Maybe I can just show you. There are probably some examples of how it's supposed to look like. Yeah, the new, prettier version would basically be in color. You would see something like this. Better than this one also. Okay. Won't work. Oh, okay. So that is basically the random forest now, which is an ensemble of trees. And by default, I think it's set to 3. And 3 is not a lot. Usually you use 100 or 1,000 trees. But then also be careful about computational performance. Often it blows up memory if we have too many trees. So I would try maybe something on a normal data set like 100, and then maybe go up and maybe look at your memory. It depends on the number of features and the number of samples, how big the memory footprint will be. Usually also you don't need to worry that much about the depth of the trees in random forests. Here it makes a difference on this data set. And the maximum number of features by default, I think, is the square root of the features. So if you have, let's say, 4 features, it will take 2 features and give it to each tree. And, no? Is it?
Each split has different features, right?
Yeah.
You said give 4 features to a tree, but
2, actually.
sorry, but it gives all 4 features to the tree, and each split individually selects 2. Total, the whole tree will use all features.
Okay.
In each node, you select 2
Yeah.
features.
Yeah,
Not
yeah.
random from all, but in each node is separately.
Yeah.
So the whole tree might use all features.
Okay, okay. Interesting, yeah. You sure?
Yes.
But is it? Okay.
That's the random forest.
Fair enough, okay. So here we basically have the 2 parameters. We use the grid search object again, the grid search cross-validation. Here it ran on all my cores. This is also a little bit dangerous with random forests, but it's a small data set, so it works fine. And we use a different number of features for as a parameter here, and we change the depth of the tree. We have a constant of 200 decision trees. And actually fit the data quite nicely, the training data, but there's still a slight overfitting because, yeah, the test score is a little bit lower. But I would say that is actually a good fit here with with a maximum depth of 9 and the square root of the number of features, which I think is a default, right?
Yeah. Default for classification for regression is long. You want to do grade boosting or maybe wrap up because we have still 10 minutes left.
Oh, so maybe what topics do we have left? Maybe you want to talk about something.
I think it would make more sense to open for general questions.
Okay. We had a feature selection, density based, yeah.
I don't really cover any of these dependents.
Yeah, I'm also, yeah, okay, then maybe let's have some time for questions now. Time is running. Time is really running, but I also feel it. I mean, it was a whole day here. I'm really, need a bunch of coffee cups, I think, after that.
All right.
Talk a little bit about what is available and what's coming in our core.
Out of core. So out of core stuff is maybe I should stand here. Out of core stuff is is data that doesn't fit into memory on a computer. And so it's currently available for linear models, particularly using SGD classifier for basic. So that's a different model, but it implements all the same things as Ridge and Lasso and logistic regression and so on. It's also available. The next version will have a relatively simple neural network. It's going to be available for a neural network. It's available for the scalars. It's available for k-means, for what's it called? Birch, which is another clustering method. So I'm not sure if it's available. So there are some feature learning things for which it's available.
Nothing on random forest yet.
No, not for random forests. I think someone is working on a Mondrian forest implementation for Python. I don't think there's anyone working on including it in scikit-learn. So you can't implement random forests out of core, but there's a thing called Mondrian forests, which is like a replacement of random forest that works out of core. But it's relatively recent. I mean, 2 or 3 years old, I guess now, and that would be good to have. But it's like not coming soon.
Could you comment on where neural networks fit into the toolboxes that you have been describing here as far as the tools?
So, I mean, neural network are mostly used as classification or regression models, and so you could plug it in for any of the classification or regression models we have here. We actually, in the next version, there will be a neural network in there that you can do for classification or regression.
So, but it will only be for now the multi-layer perceptron neural network. So things like recurrent neural networks, convolutional ones are not planned yet, I think, because it's also a little bit computational intensive. It would be more like a GPU task, like something for Theano or TensorFlow. And this multi-layer perceptron will be implemented on the SciPy and NumPy, as far as I know, right?
Yeah, so
when I looked at the code, it was.
Yeah. So actually, and I wouldn't really use the scikit-learn one as Sebastian said. So there's very good libraries out there that implement this, in particular Lasagna and Keras, and they allow you to use both CPU or GPU. I think, and via TensorFlow, you can also do stuff on a cluster. So neural networks are very compute intensive, and so if you want to really do neural networks, use one of these libraries. Probably would recommend Keras. Can I?
Yeah, just want to say TensorFlow is more like a general linear algebra library. You can think of it as more like NumPy. And Keras is basically a wrapper around it, like scikit-learn is a wrapper around NumPy in SciPy. So it gives you a very similar interface. And you can also choose between Theano and TensorFlow there. And you can also test stuff on a CPU. For example, my MacBook here doesn't have a GPU really. I can still run these things there. And then if you have a very powerful computer, you can deploy this model, change one parameter setting from CPU to GPU, and then, yeah, your model runs on a GPU. And
more practically, when would you want to apply the techniques you've been talking to today versus doing a neural network?
I mean, some of the techniques were like model agnostic. You need to do like grid search and cross-validation stuff with neural networks. Like the models in scikit-learn, so these are usually simpler to use. So I would always like try a random forest before I apply neural network, because you can just run it and it'll work. And the neural network might work better, in particular if you have a lot of samples. So if you have a lot of data points, neural networks probably work better. But they're slightly harder to get to work. So if you have and for things like the convolutional nets also work for things like images, which none of the techniques here work directly on images.
so basically, you can think of the neural network, the multi-layer perceptron, as something that we would plug in into as a classifier instead of a decision tree. But we didn't talk much about feature selection. It really depends. The neural networks, I would say, they are more specialized for different tasks. So you have different architectures, a recurrent neural network for speech recognition, like temporal data, and a convolutional neural network, which is really good at image recognition because it has this pooling of the layers that it is a kind of, not scale invariant, but scale equivariant. You don't have to worry so much about centering images. And for example, you can still use normal classifiers like k-nearest neighbors would do reasonably well, especially if you have a smaller data set maybe. But then you also have to do additional pre-processing steps like centering your image and making sure that it's centered and rotated correctly, and convolutional neural networks are a little bit more automated with that. But they're also harder to set up, basically. It takes way more time to train them. And it's basically a trade-off. It depends on the data. I think like for other things than maybe images, speech, and things like that, for typical like normal smaller data sets, normal classifiers are just fine. It's also a trade-off between computational complexity, time it takes to implement, and really having a robust API and implementation.
Then there's the other question of if you're doing it on a neural net, trying to interpret it.
Yeah, but there was actually, I haven't read it yet, but there was like 2 weeks ago a new paper, I think it was by Microsoft or Facebook or something, on the getting feature importance out of neural networks. I haven't read it yet, it's on my reading list, but people are working on that.
Feature importance is not the same as interpretability, though.
Yeah.
So, but
Would you use the same kind of train split analysis of your accuracy on a neural net as you're using with your machine?
yeah, so as I said earlier, I probably wouldn't use cross-validation if it takes a week to train. So I would only use like a train validation test split. And often people do early stopping on a validation set. So you don't have to wait, or you know when to stop.
I really want to see the guts of how this package is stretching the numbers. What's the best way to go about that?
GitHub. Most of it is, so things are easily implemented using NumPy, but most of them stuff is actually implemented in Python, which is sort of a C-like intermediate between Python and C. And so there's a lot of for loops and a lot of typing. If you look at the random forest, it's interesting. They're very highly there's like CPU cache optimized, and there's like a lot of pointer arithmetic going on. Scikit-learn is implemented in C, not in Python, basically.
So it's basically, a little bit more involved. Would be.
Other question? Okay, so maybe you can wrap it up. And you'll be around until the rest of the week, right?
Yep, I will be around. Don't go anywhere.
I won't be here tomorrow and Wednesday, but I'll be back on Friday. And for the sprints, there will actually be a scikit-learn sprint that, if any of you is interested, it will be geared towards beginner. You don't need to have contributed to any open source project. You don't need to be expert in machine learning. Everybody that wants to contribute to scikit-learn can come to the sprint on Saturday or Sunday if you're here, and you can help make the package better. Also, before you leave, maybe you can leave us feedback notes. I know people never write feedback emails, so you can leave, there's like paper here and pencils, and you can maybe write some feedback of what you think was good about the tutorial and what was not good, and then we can let you go. Thanks, everyone.